Hi, my name is Emily Ping. I'm an undergraduate student at NHERI Polytechnic Institute, and this summer I conducted a research project at the NHERI Sim Center, headquartered at UC Berkeley. My project is on the comparison of material model calibration methods using response predictions from a component model. The clicking.
I think it might be on the computer.
Oh yeah, click the screen one time and then.
And then it works.
There you go. Now I should be able to.
Okay, thank you. Okay.
Team effort.
So engineers rely on structural models to be able to simulate and analyze structural behavior under various loadings. And in this case, I'm focusing on dynamic loadings from earthquakes. Accurate models are very important to well-informed engineering decision-making and setting engineering standards. One important part of creating an accurate model is having well-calibrated model parameters that accurately represent the features of the material you are simulating. So this research investigates the effects of different methods of material model calibration on the uncertainty of the predictions of a structural component model that is incorporating this material model. So to demonstrate the difference between the structural component and the material is a longitudinal steel reinforcement bar that is inside of this reinforced concrete column. For most structural component models, the material models are calibrated individually and then put together to represent the component, because that reduces the complexity of calibration, but that also introduces error. The data that was used to calibrate the material model is from cyclic tests conducted on steel coupons, so that's a segment of this steel reinforcing bar. This graph here shows the data from this bar being put into tension and compression over and over again to represent the dynamic loads experienced during an earthquake. And the data used to evaluate the structural component predictions is from this full-scale bridge pier column tested at the UC San Diego shake table by pier. So the material model that is being used is the OpenSea's Steel O2 model. The parameters that we calibrated are in this table here. There are 3 more parameters, but we left those at their default values. We only focused on these 7. There are already a commonly used existing set of these parameters, but they were calibrated at the same time that the model was created, so they are considered to be outdated as the materials are not up to modern standards. Recent research has proposed a new set of recommended parameters that has used material that meets modern standards, but this only focused on one method of calibration and did not take into account how this material performs as part of the structural component. So to demonstrate the material model as well as the structural model, you have the model parameters, which are things like yield strength and elastic modulus that describe the material, along with the experimental data you're looking to match. And then you put it into this material model, and you will get output whatever quantity you are looking for. So here you can see some predictions of the stress versus strain curve that we got from our material model. For the structural component model, you also are putting in model parameters, but it's for multiple materials. So you have those longitudinal bars, the transverse rings, and you have the concrete. And you're also putting in the ground motions, which are going to be the shake table accelerations to simulate the earthquake. And this outputs whatever quantities you are looking for. That could be acceleration, displacement, shear force, bending moment. So the methods, we use 3 different methods for material model calibration. The first one, we attempted to match the experimental stress history. In the second method, we attempted to match the inelastic tangent modulus history. And the third method, we only attempted to match 4 values, which was the average stress in tension and compression, and the average inelastic tangent modulus in tension and compression. So this is the procedure that we went through to get the results for each method. So we performed Bayesian calibration to estimate these calibrated model parameters. This takes your prior knowledge about what these parameters might be and creates a larger distribution and narrows it down. So you need the experimental data, the material model, and the prior distribution. These were the inputs for the uncertainty quantification software QuoFem. And running Bayesian calibration, you get an output of distributions that are predictions of the material model parameters. Using these distributions, we ran them as the longitudinal bar in the system model, And by running forward propagation also in QuoFem, you can get a set of system model predictions. That is also a distribution as the parameters were. Both the material model and the system model were run using OpenSeas, which is a finite element modeling software. And Jupyter Notebook was also used to visualize results and for the post-processing of data. So here you can see the prior distribution of the stress strain curve it's very wide, it's not very close to the experimental data, but after calibration, it is a very close approximation. Here, this is the mean and the predicted range, so it is very close fit to this experimental data. This is, again, the tangent modulus before, and after calibration, it is a very close fit, not quite as close as the experimental stress, but it is still very close. And then here is just one example of the 4 values that were matched. That dark red distribution is the prior, and it is narrowed down to that much more specific blue distribution, which is the posterior, and that is our estimation of the values. So from these graphs, you can see that method 1 did the best at the material level for matching the data. Here you can see some distributions of parameter estimations. Again, method 1 does a really good job. You see it takes from that very widespread prior distribution and narrows it down to get a confident estimate of the parameter. Method 2 does not do as well, and method 3 does not do well at all for this specific parameter. This is just an example. Method 3 almost stays the same as the original distribution. It's not able to narrow down at all. So these are the system model results. We compared the 3 methods along with the updated set of model parameters from 2020. From these graphs, the updated set of parameters performed by far the best, but that's because it used a much larger data set than we did. So out of our 3 methods, method 2 actually performed the best, which at this structural component level, so for these predictions of this bridge pier column. So it's a very interesting result that method 1 did a better job of matching the values that we were looking for at the material level, while method 2 did a better job at the structural component level. So this goes along with what I was saying earlier, that the material calibrated on its own is not always a good representation of how it would act as part of a structural component or a whole structure. There are many ways to expand on this research. You could even directly use the system response to calibrate the material model. So this would give you maybe an even better estimate of how it performs as part of the structural component. You could also do more thorough comparisons of the results. We only used one structural component model, which was a simpler model. It was developed at the Sim Center by one of our postdocs. And so you could use model class selection to determine which model most accurately represents the structural component, or you could take a weighted average of multiple structural models and compare the results. This graphic here just shows you that structural models can vary in complexity. And I'll move on to my experience at the Sim Center. I also included we got the chance to see the shake table for the 50th anniversary. We got to go into San Francisco a few times. I also was taught to golf at one of our faculty barbecues, and I went on a lot of very cool hikes, which is the picture all the way to the left. So my key takeaways, I had no experience using Python, and I used that to create all my graphs and do all my post-processing for this, and it's a very valuable tool. I also learned that investigating some of the causes of model uncertainty is very important. Knowing where it comes from and knowing how to reduce it can allow us to make much more accurate structural models. And I also learned that research may not always go how you originally planned, and that's okay. It's a learning experience. But the framework of my research can be used to investigate maybe alternative methods of material model calibration, so materials can be better represented in these larger structural component models and give us more accurate results to reality. And as for my future plans, I would like to pursue a master's in structural engineering, so I would like to go to graduate school. I'm also pursuing a minor in sustainability. I would like to go down that path as well. And now that I have gained some research experience, I would like to have a more holistic idea of the field and maybe gain some industry experience. I want to thank my mentor, Akash. I want to thank Professor Letchford and Professor Lander at RPI. I want to thank Dr. Schottler and Dr. Robin Nelson for all their help during this experience. And I also want to thank NSF for their funding. Any questions?
All right, hi everybody. My name is Mitchell Gibbons. I worked over the summer at the NHERI Sim Center. Today I'm going to show you our project where we investigated the connection between emergency shelters and vulnerability. So hurricanes are increasing in frequency and intensity due to climate change. And this threatens many coastal communities and puts their emergency preparedness strategies to the test. A huge component of evaluating emergency preparedness is finding out who is the most vulnerable. And that can be determined using socioeconomic factors, geographic factors, and structural indicators. This study in particular tried to investigate the connection between what we're calling physical vulnerability, which is damage to structures, social vulnerability, which is the demographics, and then also the location of designated emergency shelters in Brooklyn, New York. So there is a disaster shelter continuum that was pointed out in the literature that I was reading that discussed how emergency shelters are foundational to the recovery and the safety of individuals during and after a hurricane event. What's important to remember is that in terms of emergency shelters, you have to think of displacement, where people no longer have a shelter or a home to go to, and so they'll need shelter in the short term after disaster. But then also those who cannot evacuate in a timely manner will need to use a storm shelter in order to be safe during a hurricane. This is kind of a lot. The main thing you want to focus on is defining the physical vulnerabilities in connection to storm surges, which is what we looked at. So there's a lot going on with hurricanes, but we only decided to look at storm surges for Brooklyn, New York. And then also defining social vulnerability, which was put in later after the damage assessment using a software called the Regional Resilience Determination Tool, or R2D tool. I know, that's a great name. In terms of both the assessment of physical vulnerability and social vulnerability, it was a binary scoring system. So it was 0 points if it did not exceed a certain threshold, and it was 1 point if it did. If it got the 1 point, then in the maps you'll see later, it would get to a darker shade of red. So the more points that a certain census tract had, the darker shade of red it would be. This is a little hard to see based on the image, but for understanding where the thresholds were for physical vulnerability, it was all based on the inundation heights relative to the building structure. So as you can see for the basements, there's this little black box at the end. Let's see if I can point it with the cursor. You guys see that?
Yeah.
Oh yeah, cool. I'm gonna do this really well. All right, right there. Those are utilities for heat and electricity, which are stored right in the basements in most buildings in Brooklyn. When there's storm surge, the first thing that floods are these basements. And so people, especially in Hurricane Sandy, were without heat and power for quite a few days. And then also, at least for this attached structure, you can see that Unit 1 is also below ground level. So very low flooding, and it would also be a loss to this dwelling unit. The thresholds assigned to those were 0 feet. So as soon as the flooding exceeded 0 feet, we assumed that the utilities were lost and the dwelling unit was lost. And those are each separately 1 point. Let's see. All right, so to simplify the damage assessment, there's obviously a large range of buildings in Brooklyn. We kept to residential structures and used these kind of generalized building archetypes, which were the bungalow, detached, semi-detached, attached, and mid-rise. Here you can see on the top that the detached is kind of just a normal single-family home, wood frame, very low elevation, So it can very quickly lose its dwelling unit and its utilities, giving it a very high vulnerability in our damage assessment. Then the mid-rise, still vulnerable because its utilities are also stored in the basement, but what was found is that a lot of the dwelling units were at least 8 feet above ground level, so they weren't as vulnerable, at least to lower levels of storm surge. In a study that we found done by the City of New York, and actually it's where we helped develop the building archetype idea, was they cataloged the buildings throughout the 1% annual floodplain, which was done by FEMA. And they developed retrofit scenarios as sort of a guideline for increasing the resiliency of these coastal communities, and also cataloged some of the vulnerabilities that we're discussing right now. So when we saw that, we wanted to implement that in our mapping as well, which just involved raising the flooding threshold for all the structures, because that's essentially what their plan was, as you can see. Yeah, as you can see here, those dashed blue lines is the design flood elevation, which is the minimum flooding threshold for an occupiable unit. And this wasn't included in our portion of the study, but they have these flood shields that they raise in order to protect the lower shop, or whatever they're assuming that is, from flooding. Now, defining social vulnerability. When looking through case studies and academic literature, we found 4 vulnerability indicators that we thought would be relevant to the study. Poverty status, those who do not have as many financial resources will have trouble recovering after disaster, but also will hinder their ability to evacuate. The cost of gas or a hotel room will prevent them from finding shelter in a adequate time period. Personal vehicle ownership, very similar thing. If you don't own a vehicle, especially in the built environments around North America, you are not likely going to be able to evacuate quickly. Age also, when doing loss surveys after Hurricane Katrina, they found that there was quite a few elderly who were not able to evacuate quickly and didn't have alternative means to assist them in evacuating quickly. And same thing with English proficiency as well. Some populations were not able to evacuate quickly because they just didn't get the messaging that was tailored to them. Now the maps, the most exciting part. Here is just the mapping of physical vulnerability. To the top left, that's a Category 1 hurricane, and then to the top right, that's a Category 4 hurricane. This is only with the 2 indicators for physical vulnerability we talked about before. So the pinkish area means just one physical vulnerability indicator was prominent in the exceeded threshold. So this was set at 50% for the basement units because we set the flood elevation at 0. And then it was 30% for the dwelling units because some of them were more elevated than others. The bottom portion is with the retrofit strategy. So bottom left is a Category 1 hurricane with the retrofits, and the bottom right, Category 4 with retrofits. As you can see, it makes a pretty big difference for Category 1 with the retrofit strategy, but when using the storm surge models that we had from NOAA, it made very little difference for Category 4 hurricane. And that was just because when looking at it, like the peak inundation height was like 21 feet. So there just wasn't much that even with those retrofits could do. Then the social vulnerability mapping. You can see that most of the concentration is in the more, I guess, south central portion of Brooklyn for all 4 vulnerability indicators. But if you also notice, there's a peninsula, which most people can recognize as Coney Island, Brighton Beach area. You can see there's a few that have all 4 vulnerability indicators, or 3, and those will be relevant later. And also in Sunset Park, which is, I would say, closer to Manhattan along the bottom west portion, you can see that there are some that also have 3 to 4 social vulnerability indicators. This one here was aggregated of all 6 vulnerability indicators for a Category 3 hurricane. As you can see, the most prevalent vulnerability is within the peninsula with Coney Island and Brighton Beach area. And that also those blue dots, we're finally getting here, are the emergency shelters. So this is a very qualitative analysis because we didn't have enough time to, let's say, map the distance from the center of a census tract to the nearest shelter, or to investigate what the actual capacities were of these individual shelters. But just by looking at it, you can tell that most of them are concentrated further up north, where there is significantly less vulnerability when compared to areas down below, which have far more vulnerability. The reasoning for this, we believe, is because they have a know your zone in New York City, where if you're in the highest zone, you get the first evacuation warnings, are expected to leave immediately. However, there is an interesting gap that, I'm going to talk about the future research in just a second. There could be an interesting gap that can be explored by figuring out if policy has actually tailored messaging for these communities to make sure that they actually can evacuate quickly and get to these shelters, which are logically further away from storm surge inundation, but also could be too far away for people to evacuate quickly based on the demographic characteristics we talked about earlier. So the limitations, it was obviously a simplified damage modeling process. Something I didn't go into earlier is that when measuring the inundation height, we only measured at the center of a census block. So all the buildings within that census block, if let's say the center was 10 feet, and there's 10 buildings in that census block, all 10 of those buildings had an inundation of 10 feet. That doesn't really account for topography change and other factors that could lead to maybe some buildings being more flooded than others. So we could have overestimated the number of dwelling units lost, most likely. Then the hardest part of this whole study was being able to use the information we had for damaged structures and then connect it in a way to demographics without being misleading. We wanted to be informational, but not go so as far as saying with certainty that if a neighborhood had 40% of people living below poverty and then 60% of the dwelling units were flooded, you can know in all likelihood there's a connection there, that there will be overlap. But from this study, you don't want to say with certainty that yes, one for one, those living below poverty will also have flooded dwelling units. So that was something we just had to be careful about throughout the whole study. Also, it was very qualitative. It was me for quite a few hours just looking at different variations of this map and playing with the thresholds and going, that's a darker shade of red than this scenario. I think I'm going to use this for the presentation. For future work, I'm all about community collaboration, so I would like to actually talk to the neighborhood associations that in this study we are saying are vulnerable and in other studies say are vulnerable to storm surge, and understand what their thoughts are on emergency shelters and their uses, what factors they take into account when evacuating, what flooding looks like for their homes and their families, and also talking to the City of New York themselves to understand what their thought process was behind the emergency shelter locations, what the capacities were, and getting a clearer picture of the whole situation. Refining the damage modeling to maybe do it at the building level, so that's more accurate. Also, I didn't add it in here, but adding more building archetypes so that it creates a clearer picture of what's actually going on, because there's a lot of mixed-use buildings that we didn't include in here, and that we would like to include, because that would make it a more accurate map. And then overall, just utilizing more indicators through more academic research, more surveys, more studying, and getting more historical data. Let's see. All right, you guys have already seen most of these pictures. The one I want to draw your attention to is me in a tree. Because that's my favorite. It was a great photo. And surprisingly hard tree to climb. The trunk was very large and the tree, it was difficult, but I did it and I was proud of myself. Let's see. My learning outcomes, this was what we call regional risk analysis. And as an urban planning major, I really appreciated all the nuances and complexities that went into this. It's not just as simple as saying, oh, here's a social vulnerability indicator, it's here and here, done, end of story, here's a pretty map. It was a lot of thought that you had to put into, and you really had to make sure that you were appreciating the fact that there's a lot of uncertainty, and you want to make sure that you represent that uncertainty in a clear and concise manner, while also still providing something that's informative and useful. I like the fact that I was working with a lot of people who are engineers and social scientists. It allowed me to gain a perspective in both fields that I thought was really useful, especially for the work I want to do in the future. And then along the same line, getting to work with all these intelligent and knowledgeable individuals was really cool for me. The more people I get to work with, the better it is. I like being able to, as an urban planning manager, I like the idea of helping build coalitions and teams to solve these massive problems that just can't be solved on our own, that require a lot of engagement with everyone at all levels of government and community to really create effective solutions. Future plans, so I got really excited about maps and statistics, and I'm taking a statistical analysis class and another GIS class this fall semester because I really want to build out this skill set and create it into something useful that I can do in the future. Let's see. All right, I want to thank Dr. Jarno Saeed, Dr. Schotler, Dr. Esnerd, and Dr. Nelson. They all contributed a lot of time to helping me with many aspects of my project, and it would not be where it was without them, and I would not have learned nearly as much without their support. I also want to thank Dr. Gavrilovich because he really helped make sure R2D worked for me. There's some times where I was not figuring it out, but he helped make sure it was up and running. And that is it.
So your vulnerability indicators were on a scale of like 0 to 1, but do you think the results would be like more accurate if you kind of scaled those more of like in a way? Is like not owning a personal vehicle kind of the same like vulnerability as not being able to speak English proficiently?
Definitely, yeah. So that's usually referred to as weights, so like placing a degree of importance on each indicator. And I wanted to do that first, but after talking to Dr. Esnerd, who does a lot of social research on displacement and social vulnerability, she was like, maybe not with the time you have, because it requires a lot of historical data to make sure it's not arbitrary. You don't want to assign a super high importance to personal vehicle ownership, only to realize specifically for Brooklyn that maybe that's not as important because most people don't own a personal vehicle and there's other means of transportation. So that was something we thought about, but we decided to not do it just because we didn't want it to be arbitrary. And we still wanted to, as before, be informative without being misleading. Yeah, you first.
Okay. I just wanted to ask you a little bit on how was the data acquisition process and what were the most difficult parts or things that the data that you simply had more difficulty in finding?
The data?
Yeah, because sometimes, at least I've previously worked with trying to find governmental data, and it's very difficult. Sometimes there is not complete data. Sometimes they're not labeled correctly, or you just have to work to find them all over the place. And I just wanted to know how was your experience in that part?
Oh, that's incredibly difficult sometimes. Emily and Carmen can tell you, I spent 6 hours one day trying to download the Army Corps of Engineers storm surge data. It took so long and only found out that we couldn't use it for the study anyway and had to go to the NOAA storm surge model. It was quite a lot, yeah. Did you have a question?
Oh, yeah, do you think like what the research you did this summer could help like inform like the funding mechanisms like into the community? And you talked about like later doing like community facing work, but like it seems like it could be really helpful for yeah.
Yeah, I think the best part about GIS and this kind of map making in particular is that it's just first and foremost an information and advocacy tool so that you can just show people exactly where resources need to go. And I think that's super important.
Hello everybody, my name is Yahya. I'm hailing from Portland, Oregon at Portland State University, and I'm a rising sophomore. And today I was working at, not today, during the summer I was working at University of California, Davis, and my project is titled Soil Compaction for the Centrifuge Model Construction. Okay, well basically, so to start off, when I went over there, basically what they were trying to research was the work that was being done was basically the concentrated leak erosion that happens in levees at the University of California, Davis. And when I came over there, basically the whole thought process was how can better compaction help achieve, a better levee with the use of a new roller as well, and what kind of tests can we do to also achieve controlled compaction? What are the differences between the wet of optimum and the dry of optimum? And basically, to conclude with that, we were trying to figure out what's the best way that we can have controlled compaction and make it more uniform, repeatable, and just, we don't have to have issues later on and, during our testing, with any guides and all that type of stuff. So on the left right here, basically, is an old roller that they had. I know it doesn't look that pretty and all that type of stuff. But as you can tell on the right, I kind of, made it a little better with 3D modeling. Thank God 3D modeling is here. But yeah, start off background. So before I begin, we got to know what compaction is. So compaction is the mechanical densification of soil by removing air voids. You could also remove water voids inside compaction. But basically, it kind of helps, make it a lot more permeable and, basically just sturdier so that, when you're building something on top of it or when you're actually building with a soil, it doesn't crumble or it's not too wet and, nothing of that type of stuff happens. And, compaction is actually controlled by 4 factors. And the first one is the in-place compaction dry weight unit. And that is basically when you take soil and you try to compact it while it's dry without adding any water. The other one is the moisture content. It's about another thing that we kind of look at in the soil during the time of the compaction. And the third one would be the consistency of the compaction method. There's different types of methods that people use, such as layer of the remodeled soil, such as the lift thickness, the consistency of the thorough material, and the number of passes. So that's another thing of the compaction equipment. I don't know why I wrote 4, but it's my mistake. And so basically, when we're doing all this, we want to have an idea of what to do with our compaction ideals with a levee. Because oftentimes, the failure of structures such as levees happens because of inadequate compaction. When you have a levee that's not compacted, what's going to end up happening? It's going to crumble or it's going to be too wet, and that's going to be a bad thing. And internal erosion is also another thing that, Mason and Anna are going to be talking about further down the line. But basically, internal erosion happens around the embankment of the levee, and that oftentimes happens because water is coming through from one side and it's going through the other side. So basically, it's happening at the core of the levee itself. And there are other factors as well that also affect levees, but we're looking at the last one, so basically the core characteristics. Because internal erosion is happening in the inside, it is going to affect the inside or the center of the levee. So basically we're trying to figure out what can we do in order to help control that itself. So to start off, before we do any of that, we got to look at our materials. So basically, what we used was YOLO loam. It's a type of silty clay that has an 86% fine content. And I'll be talking about the difference between coarse and fine content later on. But basically, it's a type of clay, and we obtained it from around the facility, and from the geotechnical centrifuge. And we also we obtained it basically from a borrowing site, and we pulverized it, and we passed it through a BS sieve number 4. So that's that on the left, right over there, and we kind of put it into a container. And Mason can tell you, it was a lot of work, as you can tell, 3 barrels full, you know what I mean? Just hand sieving all that, under the hot sun. Oh my God, I don't think any of you all want to experience that. But basically, while we were doing that, it was kind of interesting because, you could really tell with the sieve, as I learned during the summer, there's different numbers. Sieves are numbered differently. So with sieve number 4, it actually helps, get the coarse and the fine material just difference from each other. And basically that helped out with getting the type of clay that we wanted, which was clay. Yeah, basically, so the difference between coarse soils and fine soils is the fact that coarse soils you can also see with a naked eye, while fine soils you can't. And fine soils are also, when you wet them, there's a type of texture, which is basically a lot smoother and you can kind of mold it. While coarse, you can't really do that with it. And the best way since we're using fine soils, the best way for us to compact it would be with a sheep's foot roller. So basically, later down the line, as you guys saw in the introductory, I'm going to be explaining what kind of compactor we use, the whole process with that, and how difficult that was, but that's a different time. So yeah, basically the reason why we also wanted to use, there's another thing that we also focused on, such as the dry of optimum and the wet of optimum, as I explained also in the introductory slide. So basically, we wanted to use dry of optimum because in order for us to actually build the levee further on, we want to have it, we want to have a crack induced in it because we want to see if our idea actually worked out. And if we have it more wet of optimum, and you want to induce a crack, that's not going to work. You're not going to see a crack. In the end, it's just going to be a pile of mud, just nothing. It's not worth anything at the moment. Can't really work with it. But also, we don't want it to be too dry, because if it's too dry, that's also going to crumble. So we want it to be at the right consistency or density of the soil, and we also want it to have the right water content. So that's what this is basically. So we did so basically this is a compaction curve, as I learned over the summer. And basically what you have to do is, in order to find this, there's a couple steps to it. The first step is you take some soil samples, and then you put it in and then you have to pound it 25 times, basically. 1, 2, 3, 4, up until 25. And you do this for 3 samples, and then at this point you can do the mathematical equations. I'm not gonna get too much into that because that's not really my part. But basically what we ended up finding is through this graph, is that the water content is going to be at 18%. That's at the very optimum. And the dry density is also going to be at 1.64. But what we want is, since that's not, we don't want that, we want it to be a bit drier, we want to go down 2%. So we want it to be 16% water content, and we want it to be 1.60 dry density. Just for the sake of our project, since that will work out better. So yeah, like I was explaining before, the dry density side of everything, basically, if you get it too wet, there's going to be water films developing around the dry soil itself. And with that, that's not really going to help out in our project, because what's that going to end up doing is just going to make it more, a muddy texture, and you can't really build off of that. And if we want to induce a cracking, that's not going to work out as well. And then there's a density at its optimum, the water content at its optimum as well, and it doesn't increase, with water or dry density like explained any further. But then there's also the wet side of optimum, which means something that's already wet, you get it even more wet. What's going to happen? It's going to wash away. Bye bye. That's done. But anyways, we don't want that either. So yeah, we want it to be at like I said, 16%. Water content and also 1.60% dry density. Just, that's pretty good for our part. All right, so the compactor building. Whoops. Okay, yeah, there we go. So the compactor building. So first things first, what we did was we searched up, some compactors that were being used today. One of them was Caterpillar's compactor actually. And we scaled that down to 1/12 its size because we don't want a huge compactor, just it's not gonna work out for us. And so what we ended up doing was we 3D modeled it. But before that, we kind of did our measurements. So basically this is gonna be this. These are kind of what we have. This is the first model right over here. So if you wanna actually hold on, zoom. If y'all wanna look at that, here we go. Here we go. But yeah, basically this is our first model. This is the second model. If y'all wanna pass that around. Please don't break it, you kind of need those. But anyways, so basically how the compactors were built was, we did our measurements and we kind of, like I said, scaled at 1/12 its actual size. And we used AutoCAD after that. AutoCAD was our best friend. With the help of Mason Maggio, I was able to get the right measurements. I was able to get it the way I wanted to. I was able to array it. But during that whole process, we also had to look for the actual, metal part so that we can put around our compactor. Because the sleeve is important, but since it is a sleeve, we kind of need to have a cylinder inside that sleeve. So we ended up asking somebody, Chad, to help us out, and then he, cut up a cylinder to help us out with that. It was pretty heavy, but it actually worked out pretty well as well. We actually used a hollow rectangular box to kind of just fit both ends in. And as you guys can tell, there's a smooth roller in the back right over there. We didn't bring that today because we only have one piece. But basically what that helps out is kind of smooths out after the compaction is done. Because once the soil is compacted, it's kind of just going to be all over the place. So what we do is we kind of turn it around and just go back and forth with that as well. And on the very end right here is the completed compactor. All right, so our results. The first one, okay, so over there, yeah. But the very first compactor is kind of a mess, to be honest. A lot of the teeth were didn't have attachment points, which is an issue because if you put too much weight on them, there's a probability of them breaking off. So that was an issue. The other issue that we had was during the 3D printing process. A lot of the lines and the way they're supposed to be shaped was off. So when we were compacting them, we didn't have the correct compaction that we needed to. But the good thing about it was, with the soil and everything on it, we were able to actually, clean it off because as you guys can tell, there's a lot of spacing. But that's also an issue because the surface area that it compacts is a lot less compared to the second one. So basically the second one actually did its compaction well. And there wasn't any issues with it, and since there's a lot more teeth and there's less space, the compactive area was pretty well, and so basically it did its part well. The issue with it though was there's still soil being lost because it's pretty hard to take out the soil just with your fingers. We had to use a screwdriver sometimes. But basically, yeah, that kind of affected how much soil we actually had inside our container at times. But basically what we're trying to do, hopefully, is make a new compactor with not this many, but still, a relative amount where we have a pretty good compaction area. Okay, so this is a video there's another result. So basically, after we compacted our soil, it did its job, congrats to it, good job to that compactor right there. And so, let me see if I can play this. As you can tell, it's pretty hard, and it took a lot of work for it to actually get out of the soil, to get the soil out of the whole container. So that just further proves on that if the compactor is working well, and the density that we have for the soil and the water content that we have with the soil is pretty good. So that goes on to there we go, conclusion. So compaction control is actually essential in a construction site, especially since we do want to control it half the time. If we want to change a specific variable, we want to be able to change it, not dramatically, but to a point where we're like, okay, are we sufficient with this? What's the tiny changes that we can make? Do we have to reuse soil? Do we have to do a whole nother project? We want to make it pretty lenient for ourselves because, like I said, 3 barrels, we don't want to do that again. Though it's important to compact, since in the future we're trying to build the levee, since we didn't have time to actually build the levee, we want to induce cracking in it. But take my advice, you don't want to induce cracking in the actual levee because, if a lot of people end up dying or structures end up going haywire, nobody wants to have that on their backs, the grief and all that type of stuff. And the very last thing that I want to conclude was the compaction that we built was able to actually give us the desired results that we want to. So hopefully we're trying to improve on it with the whole soil clumping up issue. But yeah. So for our future research, what we want to end up doing is actually building the levee. I could be saying all this, but in the end, if I don't build the levee, it's not going to mean anything. So that's one of the main things that we want to do once we get back to UC Davis. Another thing that we want to do is to be able to induce a crack. So since we already have all the components that we need, the right type of soil, the right type of water content, the right type of dry density, and the right type of compactor, we want to be able to induce the crack in the levee. And the final thing that we want to do is see how many rolls it takes to compact. I was talking a lot about this. Basically, we kind of just rolled. We rolled with it. No pun intended. But basically, we just kept on rolling, and then we'll just feel it with our finger and be like, okay, it's compacted enough. That's not the best idea because basically you need to have, sure, there's uncertainty in geotech, but we don't want that much uncertainty. So basically, we kind of want to, be able to measure how many rolls it took and how much weight we have on it. And do we have to increase how many rolls? Do we have to increase how many weights? We can't get those figures out there if we don't have the number of rolls it took to begin with. Learning outcomes. So what I learned during this whole time, since I am a rising sophomore, was geotech's pretty interesting in general. But the first thing was research is long and tedious. I'm not gonna lie, it took a couple sleepless nights, and a couple missed meetings with Robin, I apologize, to, finally get my work done. And, I bothered a couple of my friends, Mason, Anna, but, it's long and tedious, but, you can't blame, that's just how research is in general. I think a lot of you guys can relate to that. Geotechnical engineering really shows the importance of foundations, levees, and dams, because oftentimes we overlook, what it's actually doing for us, for the beauty. Sure is holding up water, sure is doing this and that for us, but you gotta look at it. If a whole dam breaks or if a whole levee breaks, that means it's not only gonna affect a small population, it's gonna affect a lot of people. It's not only gonna affect people, it's gonna affect, the whole climate, it's gonna affect, just the structures around the area. So they are actually pretty important. So having other researchers read and give criticism is also actually really important. Hi again, hi. But basically, had a lot of mistakes, getting into this program. Being somebody just fresh off freshman year, it was hard for me to kind of get into, the actual geotech thing. Because first day meeting, I hear all these vocabulary words I've never heard of in my life. And you know what I was given? A textbook. I think it was, I think I appreciate that. But, sometimes I feel like, I did get that actual hands-on experience. So, hopefully in the future, I do have 3 more years left until, getting into grad school. But I do want to get into grad school. But at this point, I feel like I have a pretty good understanding about soils. But, I still can learn more as time goes on. Acknowledgements. So basically, I do want to thank NSF, first of all. Thank you for, funding this project. I want to thank Robin. I apologize again for some of the missed meetings, but, you were incredibly helpful. You were like, somebody I could really look up to and, get a lot of help from whenever I needed. So I appreciate you for that. I want to thank Dr. Ross Boulanger. He helped us out, even though he wasn't there all the time. He still gave us his ideas. He still gave us some feedback. I want to thank Alani, if he's on Zoom. He was amazing. He helped out. He was like my role model during that time, talking to me about compaction, teaching me all these types of stuff. Though he was very, a bit, serious. I appreciated that because it kind of put it in my brain. I learned a lot during that time. I want to thank Anna. I want to thank Mason. They helped me out a lot. Especially it can be pretty annoying to have somebody who knows zero during the site, but they didn't think too badly about me. They helped me out, and I really appreciate them for that. And I want to thank my family. I want to thank my friends. I also want to thank Portland State University. They did send out the email, and I did get this opportunity because of them. I want to thank my mom and dad. They helped me out too, and I want to thank my friends also who just kept in touch with me as well. Yeah, I forgot to include this, but my experience at Davis, as you guys can tell, we did a lot of compacting right over here. Me and Mason were up there just on some, tower and just climbing, it was pretty fun as well. That's us on our hike, the last 2. It was pretty enjoyable. I did a lot of questionable things during that time, but still we can overlook those. But yeah, I enjoyed my time. I made a lot of good friends, met a lot of new people, and yeah, I really like this opportunity. Here are my references. Thank you very much. Now we get to questions. Anybody got a question? Yes, ma'am.
So on the slide for your future research, you mentioned that you want to count how many times it takes to actually compact it. But I was just wondering, how long did it actually take you to compact it the first time?
The first time, okay, I was counting in my head, but that wasn't, I kind of missed a couple of steps here and there, so it wasn't accurate at the moment. But it took, I think, a couple minutes. That's the other thing. So I feel like, you know, with that in mind, I didn't even count like how long it took, that's the other thing. So I feel like rolling it, just having a number of times rolled, you know, having that in your head and just like putting that as a variable would really be helpful. Because, you know, in the future, you know, we can kind of be like, all right, just roll it this many times and then you're good. You know, kind of like we had with the previous compactor there. Yes, sir.
So when you talked about the 86% fines in the soil, was that just like in general, or was that kind of designated like certain percentages between silts and clay?
Oh,
Or
no,
was it
that was
just long
for
as
the,
it-
that was for the YOLO loam that we used. That was for our soil that we had.
Okay,
Yeah.
so is there like specific within that that's supposed to be silt versus clay, or is it just kind of any combination of 86%
I think
fines?
with the difference would be like there's supposed to be more silt. For us, at least our soil had 86% more silt than it did have porous, so that kind of like made it okay. Then that kind of classified it as a silt soil. So yeah.
Was there like a cap as far as like certain size grains like you couldn't have for coarse, like they would be too big for the
Oh
levee?
yeah. If they're too big, then what we did was kind of pulverize them even more and kind of make them go through the sieve one more time. And then, you know, it happens like 2 to 3 times. You know, if it's still not coming down, then we just throw it away.
I know that a lot of you have questions, but we do have to go on. So as we
One more
advance,
question, hold on.
as we go on, you will obviously have access to Yahya. I'm going to ask you to pull them aside and ask those questions so we can move on. I do apologize.
All right, thank you.
Good morning, my name is Mason Maggio. I'm a rising junior at RPI. I spent this summer at the UC Davis Center for Geotechnical Modeling, and my project was a concentrated leak erosion induced by differential settlement. So to introduce this, concentrated leak erosion is one form of internal erosion that occurs when a crack is formed in a levee. And the water, the hydrostatic force of the water forces its way into that crack, which is the concentrated leak. So this figure 1 shows many factors that can contribute to a concentrated leak. Livestock, trees and bushes, rodent activity, leakage in a conduit, but what we're focusing on is differential settlement. Differential settlement is just a non-uniform settlement across the span of a levee. So why are we looking into this? Many piping failures occur 6 to 12 hours after the first observation of a concentrated leak, and that is a rapid failure. The United States Bureau of Reclamation put out a study that said every additional 60 minutes of warning time greatly increases the chance of successful evacuation. Presently, the estimation of cracks and crack depth, defect size, shape, location, it's all made off of qualitative analysis. It's past experience, it's engineering judgment, and then it's just modeling examples. So there is currently a need to provide a scientific basis for the formation and characterization of cracks for the evaluation of concentrated leak erosion and embankment deformation. So a brief review of some similar studies. In 2006, there was a huge conference in France that was just like that everyone in the industry that focused on internal erosion. And they came to a consensus that we don't really know much about crack formation and propagation in concentrated leak erosions. Another study done in 2009 by Vindisham and Rajesh used a similar trapdoor apparatus to what we're going to be using to create differential settlement in a clay liner, which is a little different from what we're doing. But they also used digital image analysis, which Anna will be explaining in depth after me, to accurately measure displacement of soil particles over time. Transverse cracks, okay, so another study in 2010, they found that transverse cracks commonly form at abutments because of differential settlement. So an abutment is just a concrete, it's pretty much just like an angle like this where you're building your levee up. So one side of the levee will come down a little bit more, this side comes down a little bit more, and they create high stress points. This same study did find that crack severity increases as the relative density decreases from maximum dry density, which is another reason why we didn't want to hit our maximum dry density, because unlike industry, like Yahya said, we are actually trying to break this. So our design process. The first thing that we decided to do was break it into 4 major systems. So we had flooring and hydraulics, the water and circulation system, our levee and foundation, and then our instrumentation. And for each of those systems, we found a key design decision. So we had our moving and non-moving sections for our flooring. We had our waterproofing for the water circulation system, our soil type and compaction method for the levee, and then cameras versus using low power transmitters for instrumentation. In the top left, right for you guys, figure 4, that shows our actuators, which are the components that we actually use to drop our table. Figure 5 shows the FSB2 container, which is the container that we'll be putting in the centrifuge to spin our model, with a half-done waterproof liner. Figure 6 is just a picture of that yellow loam that Yahya told us all about. And figure 7 is the Photron fast cam MH6 cameras that we're using for our digital image analysis. So this is a model of our apparatus. At 250 millimeters tall, it's not a very large structure, and it's only 1.6 meters wide. So in the centrifuge, it's going to allow us to scale this to a much higher number. I'll talk about that a little bit later with the scaling factor. But figure 3 shows the 3D images. So the figure on the right for you guys, you can see the actuators are sitting underneath a section of 8020, which is a rigid aluminum apparatus, and that can travel 25 millimeters, and that is where we're going to try and induce a crack. So, talking a little bit more about this hydraulic table. So, these 8 actuators are each rated for 3,600 pounds and 3,000 psi, which might seem like a little bit of overkill, but our model weighs about 800 pounds of soil, and at 40 Gs, it's going to be 40 times that. So, directly over the actuators, each actuator is going to be accounting for around 3,000 pounds of pressure at 40 Gs. And the 25 millimeter of travel allows us to drop to our high density sandbox, which will eliminate the chance for differential settlement on the back half of the levee that we want to avoid. So we can settle the front half as much as we want. The back half isn't going anywhere if we don't want it to. Our pump system. The pump system is super simple. We just have one pump. There's 2 inlets. So we have one inlet on the dry side to try and maintain our maximum water level. One inlet on the wet side, which will be put at the maximum water level so we can keep the pump primed and circulating. And then the outlet will be on our wet side of the levee and is dampened with a sponge to prevent particle impact and disturbing the actual levee itself. The waterproofing was a very interesting experience for me. I had to do some research into some latex sheeting, and we found that a hexane-based adhesive is the best way to adhere latex. It creates a contact weld that is waterproof. And to be safe, we are also using a silicone sealant to seal the levee in as well. So for our levee construction, as Yahya told you about our yellow loam, we had a liquid limit and plasticity index of 41 and 21% respectively, and a fine content of 86%. This lines up really well with the study that Ho did in 2010, because they used a very, very similar soil to what we did. Their soil was less cohesive than the soil that we're using, so we're going to see how that impacts the cracking when we get to that. So for the compaction control, Yahya told you all about that compactor that we designed. It's based on a scaled version of a Caterpillar pad foot roller. I did some of the 3D modeling for that, but it was his brain that kind of put that all together. And then our method for compaction that we're going to go with is the method of under compaction stated by LAD. So for that, what you would do is you'll have your first lift layer, and say you're hoping to get to 90% relative compaction. You're going to compact that first layer to 80%. Then the next layer is going to be to 85%, then 90, then 95, then 100%, then 105%, because as each layer is compacted, that effect will go down to the next residual layer underneath it. So the method stated by LAD will allow us to have more uniform soil density closer to our target goal. Now these cameras. Anna is going to do a much better job explaining these cameras than I am. I just know like the very basics of them. So we have our high definition axial cameras, which are just used to record our test. They're just standard cameras that you would expect for monitoring. But the 6 Photron FastCam MH6 cameras are really cool. They use a team of software and they perform a digital image analysis. So as you can see in these, in figure 10, this is a test apparatus that Anna built. And using markers, you can pretty much place these cameras and it'll tell you how far something moves and how long it takes for these, how long it takes for it to move. So the reason we want to use these cameras is currently the low power transmitters that we would be using, like accelerometers, tensiometers, any sensor of that sort, they have to physically be on or inside of the model and can affect the data, or just the visual appearance of monitoring this system. So with these cameras, we can have them placed further back and away from the model so that there's nothing impeding our research. That's as far as we got, because we kind of got stuck with some materials issues and the supply chain was kind of bad. So we're going back to construction on Thursday, and we're hoping to get a bench test in soon. So all a bench test is we're gonna build our levee in our system, and we're gonna just see if it works. We're gonna make everything go and see how it does. And then we'll have some base data to compare to as we spin up. So table 1 shows why a centrifuge is amazing. So it just allows you to scale things at at amazing rates. So for time, flow rate, and force, it's a squared property. So we're spinning at 40 Gs. So for every second at 40 Gs, the model is actually, in real time, would be 26.5 minutes. So we can spin for 10 seconds and get a lot more data than sitting and watching a levee for a day. And same with, and then with deformation, length, and water depth, it's a 1-to-1 scale. So it's at 40 Gs, it's just 40 times whatever your value is. So our model at 250 millimeters is actually representative of a 10-meter levee. So our actual procedure. So in the centrifuge, we want to spin up to 40 Gs, but you can't really just spin straight up to 40 Gs without causing some issues. So we want to spin in increments of 10 Gs, pausing for 2 minutes just to check and make sure that there's no unwanted settlement, everything's working. And then we're going to start settling the actuators. So the plan is to settle 10 millimeters at a time, observe and see if the crack actually forms or self-heals. This is what we're interested in because there's been evidence of self-healing cracks before, but there hasn't been too much research into it. So the idea is a crack will form and the water will actually erode it quick enough that the soil collapses in on itself and fixes the crack so that there's no more issue. Then we'll settle at another 10 millimeters, see what happens then. Settle at another 5, and hopefully we can see a pipe form. And when I say pipe, it's not an actual pipe. It is water going through a soil, creating a tunnel for itself, and then as it goes through, it pulls finer, and then larger soil particles and larger soil particles until it finally collapses and there's a total breach failure. So, our future questions. Can we actually induce a transverse crack due to differential settlement? We have to try. So that's like the #1 thing for us. And with self-healing, we know that self-healing can occur, but we don't know how big of a crack will self-heal and how fast will the crack self-heal. And then we also want to look into the rate of settlement. Does that greatly impact the formation of the crack, the depth, the width, the location? Again, hopefully we're going to be getting into that a little bit next week. So my experience at UC Davis, it was actually my first time on the West Coast. I'm from Western New York, so getting used to the 105-degree weather in Davis was a little weird for me. I had in the top left, I'm standing there with an older guy. It's one of my dad's good friends. He lives up in Lake Tahoe, and he had me out, and it was like, if you ever have an opportunity to go to Tahoe, I'd recommend it. It's gorgeous up there. Yehaya had a picture of our hike. It was a great time, and he's shot. Yeah, and then canopy of trees. I love the nature up in California. It's beautiful up there. Then the actual centrifuge itself in the middle. That's me, Anna, and Yehaya sitting up on the drum, and the arm is behind us. And below that is the actual centrifuge bucket, which is massive. Me and Yehaya sitting at the top of that little concrete thing, doing a standard Proctor. And then there's a picture of me, Emily, Lindsay, and Bernard sitting on a bowl that we totally didn't take last night. My learning outcome. So my top 3 takeaways: research is a slow process, and it can be interrupted by materials very often. Networking is super important. Like all of the meetings that we did with Robin and meeting all of you guys. It's really cool to like see how networking is actually happening right now in our careers. And I found geotechnical is the right path for me. I really enjoy the uncertainty of geotechnical and the challenges that it presents. So for mitigating natural hazard disasters, hopefully this will lead to improvements in dam and levee monitoring systems so that breach failures can be prevented. Early detection can help prevent rapid progression and failure through transverse crack. If we can detect these before the crack is even formed, if we can find a stress and strain field before the crack forms, we can prevent this from happening in general. And after my RU experience, I have decided to pursue a master's, even though I didn't want to at first. And after getting my master's, I'll go directly into industry. I'd like to say thank you to NSF, the NHERI REU, Robin especially, for giving us all her time, the staff at the UC Davis Center for Geotechnical Modeling. Thank you to Professor Ross Boulanger and Jack Montgomery. A huge thank you to Alani, like he was there with us every day, doing so much with us. He's like super helpful. So huge thank you to Alani. And of course, thank you to my family at the civil department at RPI, specifically Professors Lander and Letchford, for helping me get into this opportunity. And yeah, so thank you. Any questions?
So you're saying like about the centrifuge that it can scale down things really nicely.
Yes.
But what about the actual failure itself? Is that kind of still like the same failure that you'd see at the large scale?
So the failure itself would be, because distance is proportional, it would still be like, if it's a 3 millimeter, it'd be equivalent to 120 millimeter. So it's a little weird sometimes with some of the scaling factors, because like, it's pretty much, it has to do with acceleration. So like time is a squared factor in acceleration. So that's kind of why time ends up being squared. So like, if you have something that's already like, has a lot of time involved with it, you'll get some really weird scaling factors, which can not be as useful. Like I had on the table, like you can see like the volumetric flow rate it's quadratic. Like that's not super helpful, because like if you're, it's just such an extreme number, it's not really achievable in real life. But it's better for time, just because like I said, you can get so much information on such a large scale in such a short period of time. Anything else? Thank you.
Hello everyone, my name is Anna Rabchanik, and I will be presenting the project I did at the UC Davis Center for Geotechnical Modeling facility about image analysis of settlement-induced cracking of a levee model. So embankment dams or levees effectively keep back water and control it from rushing rapidly to the other side. And as water flows through slowly, it can gather soil particles, and if the water gathers enough, it can erode an opening in the dam and making it easier for the water to go through quickly. This is called internal erosion, and transverse cracking, which they are cracks that are in the direction of the seepage, as shown right here. It stems from this phenomenon. It is difficult to predict cracking on a levee, so we want to observe and understand what is happening with soil movement when a levee is being induced by differential settlement, and whether a crack forms or heals during the process. So image analysis is simply extracting meaningful data or information from images. Previously, racks of sensors were placed above modeled projects, which blocked the view of movement and other needed information with many instruments and wires. So using cameras cleans up the mess, essentially. Having high-speed cameras focused on the areas or points that we want to observe will allow us to track and gather data, relevant data. It is important to discover a reliable setup for future models or practice tests to prioritize what is important to know about software and cameras for others to learn. And traditionally, we only know the initial and final points positions of points, but with advanced software, we can see positions, velocities, accelerations, displacements, etc. at any time from a recording. So at the UC Davis CGM, there have been tests performed with motion analysis software to determine 2D and 3D displacements. And one also had used TEMA Classic 3D, which is the software I am using, and photon cameras, but they also use lasers for accuracy. Additional researchers performed image analysis on centrifuge models of longitudinal cracking, so it's not towards the water or the seepage, where ours is. And they placed targets to form elements for strain determination. The high-speed cameras also give a simplified approach to observing the points that we want to see, and simplify model construction as well. So some key things to think about were the accuracy that the software can have to determine positions and displacements using image analysis software, the steps to perform the testing with cameras, and where the targets should be located, but mainly for the centrifuge test. The main materials used in this experiment was a 3D printed levee, which I thought to print in 2 parts to simulate the settlement that I was trying to look at as part of the testing. So one of the sides of my 3D printed levee was able to lower down, and I just thought it would be fun to have one. It was more of like the nerdy side of me that wanted the 3D printed levee. I could have just used like a book or something to watch movement. Next were the quadrant markers, using different diameters depending on how close it was to the camera view, which they were used for the TEMA Classic 3D software, which is the advanced tracking motion analysis software that can calculate positions, velocities, and accelerations using tracking algorithms. Additionally, we had the Photron FastCam MH6 system. The M stands for monochrome, and the H is for the high speed, and then the 6 is how many cameras come with it. So for the 3D displacements, you technically only need 2 cameras looking at the same points that you're trying to track to get 3D. So that's what I used. I used only 2 cameras, especially since the levee that I had was pretty small. And of course, for diagrams and analyzing data, I used Jupyter Notebook. So essentially, I first had to determine the recording duration, frames per second, resolution, and lighting in the video. Then I placed a model and targets inside a 3D system with reference points that I had to hand measure. And that part, the hand measuring, is important. But the recorded movement of target points with the Photron camera system was next, using at least 2 cameras to determine the 3D positions. I then calibrated the cameras to determine position, orientation, and of the cameras, and then lens distortion as well, because that improves accuracy. And then I also tracked points with TEMA Classic 3D software, using quadrant symmetry or correlation plus, and those are the 2 algorithms that I used to track my points. And then I calculated displacements and then graphed it in Jupyter Notebook and analyzed the data. So here's basically what the target points look like for my test. In test 1, I focused mainly on points 2, 3, 4, 5, and 6. For tests 2 and 3, since they were similar, I focused on 1, 6, 10, 11, and 12. The quadrant markers around the model are for reference points, although I did make 1 or 2 reference points on the levee just to see if it would help the software become more accurate, just because that's where I was tracking points. And so I did 3 tests, essentially to see what the software could do for a slanted object. Test 1 was 6 inches away from the 3D levee, and I only moved the quadrant markers, as shown in the video, with a string that was attached to them. And then test 2 and 3, I lowered the smaller side of the levee around 11.88 millimeters. And I decided on average, because when I was hand measuring, it was about 11.75 to 12. And test 2 was closer, while test 3 was farther. And additionally, the markers were fixed on the levee for test 2 and 3. But in reality, when the levee is lowering, the markers will most likely move in their own directions and not stay fixed on the exact same spot. Also, all tests had 6 frames per second and the resolution of 1280 by 720. So TIMA essentially calculates a volume from the given reference points that you give it, and from this point forward, if I mention 3D directions, if I forget to say like X, Y, Z just to help you guys, but X would be the longitudinal, so going this way, and the cameras are essentially right here at the end, but X goes that way, which is longitudinal, Y is transverse for, I guess, the transverse cracks, and then Z is vertically. So after TIMA calculated positions for 6 frames per second, I was able to calculate displacements and create these displacement versus time graphs. The circled markers at the end of the time indicate the results I gathered by hand measurements at the very end. And then comparing the data for test 1, the positions were not too bad, with up to a 4.1 millimeter difference. That's for positions, but the displacements were more accurate, surprisingly. But of course, this is all relative to like how much one is expecting it to move. Since there was no controlled setup really for this one, I couldn't tell you how accurate this particular setup was supposed to be. So for now, I am saying that test 2 and 3 are preliminary results because after I did image analysis, I kind of need to double check something, but it's like for the calibration to make sure that it's accurate for the cameras. But I will disregard the position measurements because it's more important for us to look at displacements. But test 2 is where I was expecting to know that the vertical displacement, at least more than the transverse and longitudinal directions. And I showed in the graph, the vertical displacement wasn't too inaccurate, although it can obviously be improved. Besides the outlier, which is target 11, which had about a 10% error. And the longitudinal results weren't too bad either until you got to target 12 in the X direction. Additionally, the target points were just one line across 0, just to see how well the software can calculate the displacement of something that doesn't move at all. So that's what the straight lines are for in the graph. So for test 3, it had the most inaccurate results compared to test 1 and 2, and there was a hiccup actually during the movement of the levee where it got a little bit stuck, and so it didn't lower fully on one side, and it lowered even more on another side. But the vertical displacements from TIMA ended up being around 14 to 15 millimeters down, where I was hoping for something closer to hand measurements, which were 12 to 13 millimeters. The graphs show that if the software also had a difficult time or needed help knowing where our target was, that's why you can see all like the zigzags on some of them compared to like test 1 where it was more smooth. That just shows that the software had a difficult time understanding where the points were due to graininess or noise in the video. So comparing the tests, not surprisingly, test 1 had the best results in positions and displacements with not much noise, which basically means the graininess and poor quality, whereas test 3 had everything the opposite. So throughout testing, the accuracy of hand measurements were actually harder with a slanted shape. I guess I should have used a book, but I guess I just, yeah, anyway. But where's the fun in like making it easy, you know? One thing I will also need to look at is the stereo angle of the camera, which it just means like 2 cameras and where they're focusing their direction on and that angle between them. Because the way I position my cameras, the stereo angle is very narrow, and so I should have made it larger for precise measurements. Although the calibration had small residuals, which is basically desired for accuracy, the displacements were okay in comparison. And then for calculating strains, it is important to have higher accuracy in displacements. So the testing definitely needs improvement. if we want to be as accurate as possible, which is always the goal. There are many types of errors also, but 3 main ones I will mention are roundoff errors, errors in input data, truncation errors, which they're basically caused by the algorithm itself due to approximations made within the algorithm, and then calibration for the cameras. So there are many parameters and other factors to be aware of that the software depends on to be accurate. The closer the cameras are from the desired track points with more lighting and less noise in the images increases the accuracy of positions and displacements. It is also very important and much more desired to practice testing with camera videos in the real testing environment that one will be doing the testing in, because I was basically in a dark little room in a corner doing my test on a table. So definitely the lighting wasn't the best in there. But even with all that, there will still be uncertainties in the accuracy. So future work includes the official construction, as Mason and Yahaya mentioned before, and the testing of the levy and the centrifuge, and then having someone implement the good practices to use the cameras and software for precision and accuracy. So it's also important to think about whether the displacement and strain are important enough after analysis from the centrifuge, whether they are critical. And then another thing I might do, I'm still thinking to do another test when I get back, and that's to deal with constant strain calculations using numerical analysis, which obviously strain varies, but constant strain elements are okay to use in smaller areas for accuracy. So learning outcomes. Image analysis allows us to observe, gather, and understand natural hazards such as slope failure, dam failure, landslides, etc. Using cameras also reduces the cost of other materials, and image analysis is very useful to us because we can track positions and displacements at any time. So I learned that research is slow, and there's a lot of trial and error in that process. I don't know, I honestly lost count of how many times I had to redo a setup for a test. Also, not everything goes as expected, and sometimes, you know, that's a good thing, you learn, and then you learn how to problem solve and come with solutions. And when you're problem solving, you also learn to be independent and come up with those decisions on your own. Another thing is I got a chance to learn something new. I got to learn 2 basically new softwares, although who knows if I'll ever use them again, but it was useful. And I also got to improve on my coding. After NHERI, I hope to do maybe another research opportunity and another industry experience. And then I hope to graduate with my civil engineering and applied math degrees, and it's master's or PhD after that. But I'm leaning more towards geotech now after this summer, but yeah. So my experience at Davis was pretty chill. Davis is a really small town, so you could probably get around in like a day on a bike. But this slide would not be an experience at Davis without a bike or a cow in the picture. So there's that. And then those fireworks are just the ones we saw at Davis during the 4th of July. And I want to acknowledge and thank NSF for the grants, for allowing this opportunity for all of us. I also want to thank the faculty and graduate student advisors at UC Davis for their help and their support. Also the faculty, staff, and graduate students at UC Davis CGM, they were very helpful and supportive as well. Yahaya and Mason, I thank you guys. You guys kept me strong when there were low days and I thought I wasn't going to get a test done. I want to thank Dr. Robin Nelson for all the help and like encouraging me every week. I also want to thank Dr. Richard Armstrong at my home university for helping me and showing me about this opportunity. And then I also want to thank my little brother because he allowed me to use his 3D printer at home to make that 3D levy. So, yeah.
questions?
Congrats so much.
So as you guys heard, I'm Megan. I go to Embry-Riddle Aeronautical University, and I'm at the NHERI REU project this summer at UCSD. So a little bit about the NHERI REU project. It's located on the LH Post outdoor shake table at UCSD, and this test facility has the capability of performing different seismic loadings on several different types of structures. It's recently been upgraded to 6 degrees of freedom as opposed to just the 1 degree of freedom they had before. The TALD project itself is a mass timber building that's 10 stories high. It also includes some non-structural aspects such as steel modular stairs, exterior facades on the first 3 stories, and interior walls for testing. So this building is going to undergo 40 to 50 different seismic loadings. These loadings include maximum considered earthquakes, also it considers design basis earthquakes, and they're really trying to obtain data about the structural resilience of mass timber elements on the project. So you're probably wondering, what is mass timber? So it's an engineered wood product that has gained popularity in the recent years due to it being a sustainable building material. Some advantages of it are it has a very high sustainability rating. We see reduced material waste due to the fabrication methods used. We also see a reduction in construction schedule, and there's a structural resilience of this material that competes with the traditional building materials on the market currently. As seen in the picture, we're kind of seeing a transition into high-rise structures with mass timber. This is a building located in Norway, and it's considered one of the tallest, it's one of the tallest mass timber buildings in the world. So the motivation behind my research is that mass timber is this new product, and we really don't know a lot of information about it. So if we're going to start to build these high-rise structures with mass timber, we need to kind of have a better understanding of what this industry looks like. So my objective for this research was to kind of identify some key elements about mass timber and identify how we can improve this industry for the future. So I did this by interviewing several different companies in a semi-structured interview style in order to obtain the qualitative data needed for my study. So I asked the companies these driving questions on the slide, kind of just to get an idea of like what their role is in the mass timber industry. This style kind of allowed me to ask these questions as well as more topic-specific questions to specific companies. So here are the companies listed. They're considered experts in the mass timber industry, and they all have contributed some way to the Tallwood project. After interviewing these companies, I was kind of able to extract these key themes about different roles in the mass timber industry. So the first theme I chose was material manufacturing and distribution. There's a lot of different products on this project, and a lot of them were donated by several different companies. The two I want to talk about first are the cross-laminated timber and mass plywood panel rocking walls. So they're the big structural focus of this research. And these products were also used because they're most popular in industry and they have good performance in past research conducted. Basically a rocking wall it centers a building after it experiences the load, so you have the load that goes, and once the earthquake's done, it kind of brings the building back to like straight. The next one I want to talk about is in figure 6, the lumber, or the laminated veneer lumber. So that's what the beams and columns are made out of, and they're used all throughout the building. And then the last product I want to, on the slide is the glue laminated timber. That's one of the floor panels for one of the floors. We also use the nail laminated timber, dowel laminated timber, and the mass timber panels. They all kind of have slight variations in manufacturing styles, how you fabricate these different products, and even things like aesthetic ratings, but they all provide a structural resiliency for high-rise structures. Okay, so this building's gonna go under 40 to 50 different earthquakes, a lot of them like the maximum considered, so like these are kind of earthquakes like you don't really see, they're kind of like once in a lifetime. So the traditional connection types we see in industry weren't gonna cut it for this project, so I really had to do some digging, and they were kind of given these like unique design constraints that they had to consider when designing the structure. So basically all these connection types shown up here are very unique just to this project. They all like allow a greater range of motion for all the different earthquake loading they'll undergo, but they also still provide a structural rigidity needed for high-rise buildings. So the next theme I chose was prefabrication. So usually you see in traditional wood construction, you send all your material on site, you have people cut it on site, and there's a lot of error left up to just the workers on site. But in mass timber, they use these machines called computer numerical control machines, which basically minimize error because you're programming a machine to cut the dimensions according to the design plan. So at the fabrication factories, you can cut things like floor panels, beams, columns, you can drill and cut holes into the panels if you need, if you have like things like mechanical, like things that have to run through walls and stuff. And they also can like add like aesthetic properties to it as well. So this picture here is a CNC machine that we got to visit in Portland. What's unique about this machine is it has 5 degrees of freedom, so you can make very complex cuts for complex projects if need be. And that's kind of the direction they're moving towards within industry. So the next theme is construction. Like once all these structural pieces are fabricated, you can put them up pretty easily. So what's unique about the construction for this project is it's this thing called balloon type construction. So basically you have all these continuous members that everything else gets attached to, and you kind of just keep building and building until you get to the height you want. So I'll kind of explain the process so far. So you kind of start with the foundation seen in A, and then for this project, we put the modular stairs in place because the building kind of gets built around these stairs since they're a non-structural aspect. And then the columns go up and they get braced to the foundation. And then next you have beams that get put in place for the first floor, and then the first story floor panels get put. And then you kind of do that same process for the second and third story. And then you also have to fly in like the third set of stairs so they can access that next level. And then it's not shown because I haven't put them in yet, but the last step would be to place the rocking walls in place. And then from there you can keep going because they build it in 3-story increments, so you would build it in 3-story increments as you go. And it honestly makes like the construction time like reduced, and you don't really need the amount of labor compared to like traditional projects. So like on our project, we did the first 3 stories in like 3 weeks and with 6 people, so it was really reduced. So talking about the themes that I found, when I was interviewing these companies, they kind of were all telling me the same thing, is that like, mass timber is a growing industry and it's expanding every day. As we can see in the graph, mass timber buildings in North America are projected to skyrocket significantly. And in order for these companies to keep up with this demand, we need to implement tools to help them like make decisions on projects. So a potential tool to be developed is to make these more complex building information modeling systems. So BMI, basically it allows for all aspects of a project to be compiled in one place, so you can make more informed decisions about like different projects, like decisions basically. So in the figure, we can kind of see like you can take aspects like structural analysis, code and regulation, the structural drawings, and even like the construction scheduling, and you can kind of have it all in one place on a project. And because mass timber is such a new concept, in order for this idea to kind of take off, we need to fill in more gaps of the literature. So with the available knowledge from the industry leaders and past and occurring research, mass timber is a sustainable alternative, and it's projected to be a major competitor against traditional materials. Just because the material is new to the industry, but it's also very crucial that we have research to develop the industry. And the NHERI Tallwood project plays a major role in that development because it's really focusing on the seismic resilience of mass timber used in high-rise structures. And it's going to be a foundation for creating structures that are resilient and sustainable. So here's kind of like my experience at UCSD. I honestly really enjoyed my experience. This is my first time on the West Coast, so that was really fun, and I got to meet some incredible people on site and just be able to have my RU fellows. You know, this kind of work is really rewarding because as we progress in mass timber, the industry is just going to keep getting better and better. And honestly, this research will be the foundation for providing seismically safe and sustainable structures to the public, which, you know, like we need to start moving towards more sustainable options just with how everything's going. But we also need to be considering people in high seismic or like high risk regions. You know, I've learned a lot about the mass timber industry and its inner workings, as well as just like general construction practices with high-rise structures. I didn't know a lot about that before I started this work, so that was really neat to see like how these things actually like work in real life. I was also able to improve my soldering skills because we were tasked with developing the instrumentation wires that will like go on the building when testing happens. And you know, working on this project really solidified my initial reasoning for studying to become an engineer, and it makes me really excited about my future master's education and career in the civil engineering field. So first, I'd like to thank NSF and NHERI REU for funding my opportunity to conduct this research. I'd also like to thank Dr. Shilling Pei, as he's the PI on the project, as well as Dr. Lely Vandenay and Dr. Robin Nelson for their guidance and support at all stages of this research. A special thanks to Dr. Siddharth Parida for helping me get involved in this program, as well as all the professors in the civil engineering department at ERAU, because they support my education tremendously. That's the only reason I'm here. So I'd also like to thank my friends and family for their unconditional support. And I'd also like to give a big thank you to all the companies that are participating on this project, because without their time, energy, products, services, and donations, this NHERI Tallwood project would not be possible. References. Questions?
Just out of curiosity, do you know if there's any initiative towards like also thinking about like fire safety and fireproofing, like mass timber?
So they have done research on that. This project doesn't focus on it, but I've done a little background with that. So they have like a 2-hour fire rating like code in place already. Basically what happens is you allow this outside layer of wood to get charred, and that char becomes like a protective barrier for it. So what they do in design is they'll say, okay, like we need to add an extra 2 inches to all the dimensions of a column, and that kind of is like the fire rating for it.
So I know like the mass like timber industry is all doing stuff, but do you know about like maintenance? Like is it cheaper than the other kind of construction materials?
I think there's not much research on it, but that'll probably be the next step in seeing how like what's the lifetime span of these buildings.
Can you go into rooms real quick? I just want to see what one of them was. Sweet. Thanks.
You mentioned how like the fabrication of mass timber can reduce the worker error and variability, but I'm wondering like how's the variability in general for mass timber since it's wood product?
Can you elaborate on that?
Like, I don't know, the different woods can change properties a lot.
Yeah, so they have, but like, there's been a lot of debate on like what kind of wood products to use, but they've kind of found, that's kind of what they research is like, more like what materials are gonna perform better. But they've kind of found that they have very similar properties at this point, so they can kind of like interchangeably use the different wood products. But I think like as we develop this research more, like they'll figure out like, okay, this one's stronger, or like this one has better performance with like low-rise structures or high-rise structures, like things like that. you.
So if you guys aren't excited about cross-laminated timber and mass timber in general yet, you should be. Okay, my name is Abby, and I did my research this summer on finite element modeling of cross-laminated timber, or CLT panels. Like Megan told you guys, we were working on the CSD shake table, where we're building the 10-story mass timber building. I think it's cool because most timber buildings right now only go to 4 stories, so the fact that we're going to 10 stories is just really awesome. And the shake table itself is cool. She mentioned it has 6 degrees of freedom, so it can go in all directions with pitch, roll, and yaw as well. My focus, though, is on a specific area of mass timber called cross-laminated timber. And what that is, I'll go into more detail later, but you can see it in figure 1. You stack panels of timber and you glue them together with adhesive. So the way it works, and the reason that it's good, is because normal timber has grains that go in one direction, which make it a lot stronger in one direction than the other directions. And cross-laminated timber, like, kind of reduces the limitations of that by placing panels in both directions. So now you have strength in both ways. And you can see in figure 3, basically you just lay like panels of like 2x4s or 2x6s next to each other in a row, and then apply a layer of adhesive above that, and then keep doing the same thing. The reason that this is important and the reason that we want to do this is because ideally we'd be able to start replacing materials like steel and cement in tall structures with mass timber because it's more sustainable. As you can see in figure 4, the net carbon emissions is significantly lower. And yeah, so the problem right now though is that we only see cross-laminated timber in flooring and walls and short structures for the most part. And that's kind of because we know a lot about its properties in out-of-plane bending, which floors see, and shear, which you'll see more in short structures. But what we don't know a lot about is the in-plane bending properties of cross-laminated timber, which is important, and you'll see in figure 5. Basically what this is saying is that tall structures experience higher bending moments due to like lateral forces. So earthquakes, wind loads, which we see a lot. And so if we want to build taller walls, taller structures with CLT, we're going to need to know more about the in-plane bending properties of it. So what I did was I spent the summer developing a model in Abacus to try to learn more about the in-plane bending properties of cross-laminated timber. I chose Abacus because of its abilities for nonlinear analysis and contact analysis, which are important because when CLT moves in plane, it's a nonlinear interaction. And the contact analysis aspect is important because of the adhesive between layers that we're seeing. That gets pretty complicated, and Abacus is good at handling that. So, the way I did it was first I tried to create a really complex model that had everything that we needed, and it didn't work at all. So then I created a linear elastic model, which is a really simplified version, and I ran analysis, troubleshooted a lot, and then in the future we'll increase the complexity of the model. And the linear elastic model, the way that I made it is basically I created the parts just like 2x6 boards basically. I assigned the material properties, which are linear elastic properties. So instead of applying wood properties to it necessarily, it's just elastic, simple, basically. And then I assembled them into the panel. So as you can see in figure 8, just kind of applied them next to each other. Assigned hard contact properties between the planks, which you can see in figure 7. It basically just means that between 2 planks on a layer, they'll just interact like it's a hard contact. And that's because when CLT is made, they don't put glue between the boards within a layer. It only goes above each layer. So then after that, I assigned the interaction properties between the layers, which that's where the glue normally goes, but instead of doing cohesive properties, I just did a tie constraint to keep it simple for now, and that just kind of like sticks it together, keeps it tied together. Then I added boundary conditions and loads, which you'll see in a little bit, created a mesh, and ran the analysis. So here's what it looks like. You can see the boundary conditions on the left side, and then the load, the pressure load was applied on the top, going downward. And the way it acted was as we would expect, for the most part, given this stage. You can see the stress, this is showing stresses, and you can see the stress kind of is reduced in each board and a lot of that's probably going to friction or things like that. And so that just kind of tells us that we're on the right track and it's acting correctly. And then the next picture over, the third picture, shows what the panel looks like cut in half. And so you can see what the boards going the other direction are experiencing, and that's also what we'd expect. So it just tells us that we're going in the right direction. So the current model is an elastic model, which is actually proving to be pretty accurate, despite the fact that we don't have actual wood properties in there yet. And right now it's just shape and behavior focused. So there were numbers for the stresses on the previous slide. We're not looking too closely at those because right now we're just focused on making sure it's acting the way we want it to. Which means like there's a little bit of slip between the planks that don't have glue between them where the friction's acting, and there's little to no movement between the layers where the adhesive is. Future models hopefully will be inelastic and will be more focused on the strengths of them, and obviously we're expecting the strength to be higher than like regular timber. So in the next few months, hopefully we're going to be working with the United States Department of Agriculture, or USDA, Forest Product Laboratory to get actual cross-laminated timber panels and test the in-plane bending properties of them. So we'll set up their model, like I set up my model, or vice versa, to kind of have a similar testing, and we'll actually get to compare the results and like improve the accuracy of both of the tests. So that's really exciting, and maybe I'll show you more about that in the future. And then also, as I've mentioned, we're going to keep increasing the complexity and accuracy of the model interactions. So what I've learned is that modeling is a long-term and iterative process, and like everyone's been saying, it takes patience to do research, and you run into a lot of problems, but it's fine. And we've seen that even a simple model can give good indications as to the expected behaviors. So from my experience at UCSD, we've done a lot this summer. It's been really fun. The top row, the top two pictures show us at the grand reopening of the shake table. The next top two pictures are us exploring the site. There are a lot of snakes on site, so we have to be aware of those. We haven't seen any yet, but they're around. The middle row is more of our hands-on experiences on site. So the first one is kind of me working with abacus and modeling. The second one is there were around 700 sensor cables that were tangled when we got there, and so we spent a couple days untangling all of them and rewrapping them for the future. We also got to solder a lot and tour timber labs up in Portland, Oregon, where a lot of the prefabrication is happening. The bottom row is just us exploring Portland and San Diego. So the biggest thing I've learned is abacus. I've learned a lot about abacus in this process. I've also learned that mass timber is really cool, and it's just going to keep getting bigger and bigger in the future. I also learned to start simple, because if you just try to go all out with everything all at once, it just probably won't work out, and it's really frustrating. So start simple and keep, increasing complexity as you go on. And I've seen a lot of the realities of construction while I've been on this project too, because we're watching the building go up while we're doing our own personal research. And they run into problems probably every day, and they solve them on site and figure it out as they go. And it's been really cool to watch it actually happen live, because nothing goes as expected all the time, and you really get to see that on a project like this. I would like to give a special thanks to my mentors, Dr. Shilling Pei and Dr. Lily Van Den Einde, who have been so helpful and just there for us throughout the whole process, as well as the PhD students who are on site, because they answer a lot of our questions all the time, and of course Dr. Robin Nelson for being there throughout the whole process for us, and the National Science Foundation for funding this research. Yeah.
So when you mentioned that you use like ties in the model, like how would it compare like if you were to try and model it for if you had like put nails in to like connect the boards as opposed to the glue surface?
That's interesting. It's in abacus. So instead of having because I think if you were to model nails, there would still be like movement, kind of, but it might be more like, honestly I might be modeling it more like there are nails than like there's a glue layer. But what it does when you do a tie constraint is it'll just like stick it, like kind of no matter what. So it's acting as like one unit in that way. So closer to nails, but I think a little bit more secure than that.
When we talk about like mass timber becoming more popular like in later years, and you also mentioned how it's more sustainable. Like you brought it up in terms of like carbon emissions, but I guess in terms of like deforestation and stuff, how is that being taken into account?
Right, yeah, I thought about that too in the beginning. I was like, we're cutting down more trees to be more sustainable. That's strange. But I think it's because trees can be replanted, so it's regenerative, and it's the only material like this that we can keep regrowing, whereas cement and concrete just kind of keep taking from the environment. No more? Oh, yeah.
Your 10-story building with all the wood, I see a lot of staircasing. Is there an application for elevators or?
We don't have any room for elevators.
So they have to take the 9 flights to get to? Wow.
Yeah.
Okay.
So the next interns who come on the project and are applying the sensors,
Yes.
all around, yeah, they're
I
climbing
was
10
thinking of the
stories.
people that, want to have something like a piano in their place. So.
Well, in the future, they can make the buildings bigger and stuff, but this
Yes.
one, it has to fit on the shake table, so there's limited space.
Thank
There's
you.
stairs.
Oh.
Okay, thank you.
Alright, hi, I'm Sophia David, and I go to the University of Massachusetts Amherst, but this summer I had the opportunity to work at UC San Diego at the Large High Performance Outdoor Shake Table. And so for my project, I'm doing the dynamic modeling of a 10-story mass timber building under earthquake excitation. Our project is on mass timber, which is an engineered wood, which is environmentally sustainable compared to like steel and concrete because it's less carbon emissions and it's a faster building process. So this building particularly is looking at cross-laminated timber or CLT and mass plywood panels or MPP, and I'm specifically going to focus on cross-laminated timber. So the project itself is 10 stories tall wood, which is based off of the two-story test from 2017, which looked at, obviously, the two-story test. And what they basically concluded from that was that they don't really know what's going to happen with these rocking walls at the 10-story level. So that's what they're looking at with this for earthquakes. And so like the aim of this is like if they're successful, this is like new opportunities and market possibilities for mass timber. So what are rocking walls? Rocking walls are these mechanisms that like literally rock like this, and like basically the whole point is like to dissipate earthquake loads. And so like NHERI tall wood, like I did already mention, uses CLT and MPP rocking walls, but again, I'm focusing on the CLT aspect. So my research is again on the 10-story building and modeling it on SAP 2000, which is a FEM software or finite element modeling software. And that's because like these designs aren't readily available to design engineers, and we need that if we're gonna like go forward with these projects and keep using rocking wall systems. So my question that I'm trying to answer is, can a simplified dynamic model using commercially available software, SAP 2000, accurately predict the size and performance of a 10-story CLT rocking wall building? So basically to model this, I kind of broke it down to like 7 steps that I'm going through that I like went through to build this model. So the first step was like just the dimensions and the properties, like really like base level things. So we looked at the floor plans, and like here you can see the floor plans for level 2, and that's how we got like the locations of all like the building or the parts and like the dimensions. And then I got these properties from our mentors. And then the next part is the gravity frame. So the gravity frame for our building is the beams and the columns. And like on the left you can see like it in actual life, and then on the right you can see like my version of it in SAP. So the next part is the shell element, which for us is the 2 rocking walls, where the green is the CLT rocking wall and the blue is the MPP rocking wall. And then your floors or the diaphragm, which are seen like kind of looks like a dark blue, like black color. And so these floors, though through in the actual building, they're all different types of mass timber, but on mine they're all CLT. It's modeling the UTP element, which is like the element in the actual building that helps like keep the rocking wall like in plane. And so for our building, that's modeled using like a rigid beam at the center of each story, and then these 2 link elements at the corner of each, linking like the beam, which is connected to the rocking wall, to the bounding columns. So the next part is the shear key, and what the shear key does, it stops the rocking wall from bending out of plane. And so for us, that's like a little metal piece like not in actuality it's like C, which goes into like A, but in the figure, in like my diagram, it's a little like metal piece that holds the rocking wall into the diaphragm. So these are the connection types on a building, which are super unique to our building. So if you can see in A, those are the pin connections at the bottom of each of our columns. And then if you can see in B, those are like kind of the connections on each of our rocking walls. And so this is like the full scale model when you actually put all of these elements together. And so the next part of this is like actually running ground motions on this to see if this works. So for my experiment, I used these 5 earthquakes, and then throughout this, I'm going to be specifically focusing on Kobe earthquake. And so here you can see the acceleration, velocity, and displacement of this earthquake. And then this earthquake was then scaled to design using ASCE code. And though to clarify, this building is definitely at UC San Diego, it's made for a location in Seattle, Washington, with risk category 2 and site type B rock. And so then what do we do with this information? We run a time history analysis of the earthquake at 3 different levels, being the service level, the design base level, and the maximum considered earthquake. And so the results that we get from this are kind of cool. So on the left, in A, you can see the displacement of Kobe at the maximum considered around 10 seconds, which is about when peak acceleration is happening. And then at B, which is the end of the earthquake, that's what you want the building to do. You want it to like rock back into place at the end. And then in figure 18, you can see the displacement like normal at peak acceleration and then exaggerated at peak acceleration. And so then like with those results, we want to calculate interstory drift, which is the like motion between every story using like the roof displacement and the floor of each story. And then so from that, you get your results for the service load, the design based, and the maximum considered. And then that all goes into graphs like these, where you get your interstory drift of the first floor, which for us, or for mine in particular, ended up having the biggest interstory drift. And then the 10th story had the smallest interstory drift. So what does that really mean? So using data from the University of Washington, which also made a model with different simplifications and different earthquakes ran on it, we got like the following results to compare. So like the yellow, the red, and the blue are my earthquakes, and like the interstory drifts that I got, and then the green and like the grayish color are what they got. And so you can see that they're like similar but not exactly the same. So then what does that really mean? We both use different simplifications, like I did say, and because of that, like we do get discrepancies between the two of them. And the results, until we're able to run this test in February-ish of 2023, we won't know the accuracy between these two. And like hopefully this research can be used for design engineers so that they can mitigate these effects in the future. So the future research is to compare my model once this is run and make sure that my model actually worked. And if it didn't, is to go back and work on this model and make it so that it can produce these rocking wall elements that we want. So this is my experience at UCSD. So I kind of just have a whole collage of things going on. So like there's like us doing the wires and like us on our trip to Portland and just kind of exploring around the city, which was like so much fun. And then my learning outcomes were patience, like you're not always gonna get what you think you're gonna get. And so like in these pictures, I know it looks like crazy, but this is when I like did not know how to model a building and I was getting like the wackiest results. And I just thought they looked really funny, to be honest. And like, I don't know, it was just kind of part of the process. Like I would run these earthquakes and I would get just crazy results. And then I figured it out, And then my next outcome was like learning from new people and new perspectives. So like here you have us learning from like different people on site and like getting to know each other and like learning from all the views we have coming from different universities. And then my third learning outcome was how to solder. This is me soldering. And we did that like for a couple days, and like that was so much fun. And then where am I going? I'm about to be a senior, so I'm going to finish my undergraduate degree in civil engineering, and then I'm going to apply to master's programs. And then for my acknowledgements, I'd like to say thank you to Dr. Shirley Pei at like our PI, and then Lily Vandenide and Robin Nelson for all of their help throughout this, as well as my family and my professors back at home, and also NSF. And these are my references.
So my name is Alex. Allison Vermont, and I'm a civil engineering undergraduate going into my 4th year at the Georgia Institute of Technology. Today I'm going to be presenting about the exploration of the utility and accuracy of Apple iPad LiDAR technology. So it's kind of a mouthful, but we're going to break that down really quickly. So what is LiDAR technology and how does it work? So LiDAR stands for light detection and ranging. So if you know how sonar works or radar, it's the same thing, but we use lasers. So it is used to create, you're good. Okay. It's used to create 3D models of indoor and outdoor spaces by calculating the time it takes for a laser to hit an object, bounce off that object, and be received to a laser receiver. The process is repeated millions of times in a singular location, and it builds a really cool 3D point cloud detecting the space around it. So the word point cloud is really important here, and we're going to use that throughout the presentation. This image here just shows a point cloud that was collected, and this is actually exactly what the point cloud looks like that I did all my analysis off of. So there's many uses of LiDAR all around us. You see it in automatic vehicles like Tesla, climate change modeling, robotics, as well as GIS scanning, specifically for coastlines. But the way that we use it for like LiDAR technology in the reconnaissance field is it's used by researchers to detect and measure things before, during, and after natural hazards occur. It's also used in forest inventory, and I looked into a really cool study that showed someone using a LiDAR scanner to check out the circumference of different trees in a given space. Okay, sweet. So, but what are some limitations of terrestrial LiDAR? So there's different kinds of LiDAR. There's TLS systems that are static and TLS systems that are mobile. So one example of a terrestrial LiDAR system that's static is the the Leica RTC 360. One issue that it has is that it cannot see around obstacles. It has a line of sight view, just like we have. We can't see through walls, we can't see around corners unless we physically move to be able to visibly see those obtrusions. So here we have an image of a corner that I actually did all my research on, and you might be like, wow, this is kind of a weird place to do your research based off of. It's because it kind of puts into a nice little package a lot of different obtrusions and obstacles that researchers would face when actually measuring different components of a site. Doors, reflective surfaces, bricks, cracks in concrete, corners, and as well as multiple turns. So it's a complex space, even though it's not the most exciting of spaces. So then here, this orange space that we see, that is what we call a gap in the point cloud. So it's behind this wall over here. That's where that is. If that makes sense. Okay. So Apple in 2020 released their iPhone 12 Pro and iPad Pro, which include this integrated LiDAR technology. So one of the things that we really would like to look at is what is the accuracy of this LiDAR technology and how can it be used for researchers in the field, and how good is it for collecting quality data that's also representative of a space. So if you have the phone with 3 cameras, you actually have a LiDAR device in your pocket right now. Okay, it's not working. Okay, so we have some overarching questions that we're going to answer. What are the various situations in which LiDAR technology can be used to gather useful data, and then how reliable is that data in comparison to a very typical scanner, the Leica RTC 360? So some of the materials that I used with this were an iPad Pro with the following apps: Pix4D Patch, Field 360, 3D Scanner app, and Scaniverse. The first 2 are applications that require licenses and are actually they came with the program. So we have licenses as the NHERI Rapid facility. And I don't know how difficult those are to get, but they are somewhat commercial as well. Then the 3D Scanner app is free in the App Store, as well as Scaniverse. Then we have the Leica RTC 360. I'm considering this to be my basic, like, normal measurement. It has an accuracy of 6 millimeters at 10 meters, meaning if I'm 10 meters away from a flat surface and I'm orthogonal to it, perpendicular, it can measure everything on that surface with an accuracy of up to 6 millimeters, which is very, very impressive. It sits on a tripod, it's about 6 feet tall, and it takes photos as well as collect a 3D point cloud of a space. You have to hide behind a wall or underneath it while it does this. And I took my scans for 2 minutes and 42 seconds. So I took 5 scans in one place. So the way that we went about data collection was imaging, processing, and comparison, and wasn't always linear, but this is a general process that I followed. Okay, so with imaging, I'm going to show a video of and the videos aren't working. I don't know what to do.
Are you using the pad? You're using my computer, we're not using the computer at the back, that's the problem.
Shoot, oh, that's me being silly, okay.
Sorry, it's, like I said, it's got a lot going on, so.
Okay, fantastic. So what I did was I collected one scan of the entire space on 4 of the different applications on the iPad using a snaking method, starting at the bottom of each wall, going up, shifting over, back down, because I didn't want to repeat the points that I just collected to not mess up with the georeferencing of the application itself. And then with the Leica RTC 360 scanner, I took 5 scans with overlapping point clouds, meaning that there were some defining features that they could link up to in Register 360, which is just a program for linking point clouds together. So here's a quick video of locations 2 and 6, and then here you can see some targets. And I think Anna used this in her presentation too, but targets just help you align yourself when you're actually going about aligning your point clouds to one another. Okay. So processing the point clouds, like I just mentioned, this is the process by which I aligned them. So I took each of the setups and I arranged them in the point clouds. So some of these are from iPad data, the orange is from the Leica RTC 360 data, and I will get into that in the next slide. But this is kind of cool. This is what it looks like in Register 360. So with processing the point clouds, in order to test the quality of the data, and I considered the Leica RTC 360 point cloud to be representative of the real world, like I mentioned, because it's so high resolution. So what I did was I wanted to create gaps that I could control the complexity of, the size of, within the RTC 360 point cloud. So I basically took one puzzle, I removed a piece from this puzzle, I took another puzzle, removed the very same corresponding piece, and tried to take this piece and put it into that puzzle, if that makes sense. So I had to see how well the piece from a different puzzle could fit into another puzzle using rotation and displacement. So in other words, I filled gaps with corresponding iPad point clouds and aligned the point clouds to one another. And then I calculated the overall displacement and rotation. So for example, for removing scan 3, I removed it from the RTC 360 data, filled it with the point cloud from any of the apps, all of them actually, very tedious, aligned it to the adjacent scans, and then considered that to have one obtrusion, meaning it had to look through one door in order to get to an approximate scan. So like removing scans 2, 3, and 4, I would have to go through 2 turns, 2 doors, 4 total obstructions. So some of the results from the Leica RTC 360 are as follows. This is me within a 3D image. It takes a really cool and very detailed image after it's done collecting its point cloud. And then this is me within the point cloud itself. I love it because it's just such a cool way to imagine yourself inside of a space, and just using like virtual reality concepts over here. As you can see, it's pretty detailed. It picked up just about every single surface that it was presented with, except for those minor like holes in the point cloud. So now here are some results from the iPad. This is what the scans looked like. So Scaniverse did a pretty decent job. It completely did miss a door, but that's okay. The 3D scanner app, it missed a good chunk of the ground. But then again, that's okay, this is an iPad. So I'll let you guys kind of take that in for a second. Okay, sweet. So now you can kind of see some more data from Pix4D Catch and Field 360. Field 360 is obviously the worst, I would say, in terms of presentation of data. It does not look great. It's not very user-friendly. In Pix4D Catch, you can kind of see the line I walked with the iPad, just taking those scans. So now to talk about some average displacements. Rotation is really important and average displacement is really important because the more you move away or the more you shift one point cloud from another, the greater the displacement is going to be overall if you create bigger gaps. So like, as you can see here, if you remove one scan, you're not creating that big of a displacement. But if you're removing 2, your displacement increases, 3, it increases more, and 4 increases the most. I would like to point out here the quality of Scaniverse as well as Pix4D. So this is just average displacement shifting in the X, Y, and Z direction. I know there are only 4 points, but these points are loaded. So the data from each of these 4 points includes millions, if not thousands, of point cloud information. It is measuring every single point and the displacement from this point to the point on the Leica RGC 360 data for every single point in 3 different dimensions. So then average rotation is doing the same exact thing. And so again, look at Scaniverse and how that R-squared value is looking really pretty, meaning that it fits a pretty linear trend. And then again, we see that increasing to about more than 2 scans, there's a lot more variation within the average rotation. So my main takeaways. Removing scans decreases the accuracy of point cloud registration. So more obstructions removed is equal to greater offsets in rotation and displacement. And calculating data with up to 2 obstructions should be the limit of iPad-based scans. So if you are looking for spatial visualization as a goal, all the apps can meet that. Field 360, not so much. And Leica RTC 360 is obviously the gold standard. However, you do lose a lot of quality in your data if you are replacing like big spaces of your gaps. So a couple of different things that this really opened up for us was, does point cloud size determine overall quality of data? So as you can see, the Leica RTC 360 device produced 400 million points, whereas 3D scanner app was 4 million. Yeah, Pix4D was 3 million, and then Field 360 and Scaniverse were significantly less. But Pix4D and Scaniverse had pretty good data overall as from that last slide. So some of the questions that we're asking are those more selective with the points that they choose? There's nothing that we know about either of those softwares because it is startup culture. So startup culture, they're obviously not wanting to necessarily like tell us what goes on behind that black box of theirs. So we don't actually know, is meshing occurring? Are photos being overlaid? Are averages being taken? It's kind of a big question up in the air still. So I'm gonna talk about my summer in Washington a little bit. I had a wonderful time with Summerall and Keeley. We had a really good group of girls. It was very adventurous. Here's a photo of Mount Rainier that I went hiking in front of. Here's an alpine lake that I went backpacking to. Here's another alpine lake that I went backpacking to. Yeah, it was just absolutely stunning, and we had a really good time at Rapid. It was beautiful. We had a great time being able to use different kinds of equipment. And the whole purpose of Rapid isn't necessarily to analyze anything other than the application of equipment for the use of field research and reconnaissance. So we're focusing on technology a little bit less than we are focusing on technicalities like everyone else was. Okay, so some learning outcomes. I obviously learned how to use some technical databases like RTC 360 devices, Register 360, Cloud Compare. But I also learned that research does take time and commitment to a lifelong living of life, whatever, curiously. The process of conducting research is also not linear. So when I imaged and then I compared, and then I would image again, compare again, redo, retake images and scans and point clouds, and it was very convoluted, but it's not ironed out perfectly, as you all know. So again, kind of just backtracking, how can this research be used to mitigate natural hazards? It allows researchers to scan difficult terrains to make more comprehensive spatial models if they can fill in those gaps that exist. It saves time, it saves money. It allows people to take a very small piece of accessible technology. It removes the barrier of entry for researchers all around the world to collect quality data, but also collects data discreetly. Sometimes when researchers are traveling to new countries, having a 6-foot tall thing on a tripod that spins and makes noises is not always the best way to go about handling a new culture and situation. So post my NHERI REU plans, I would love to get a master's degree in the realm of civil engineering, but I really want to do backcountry research, the kind of research where you go with your equipment to the middle of nowhere, you measure things. That would be very much a spark of my joy. I'm clicking.
I think the batteries are going.
And yeah, it is. So some acknowledgements I'd like to make. You obviously all can read, but Dr. Cha has been my lifeline through this. He's been pretty great for me. Just being exceptionally patient and exceptionally patient and giving me very quality guidance throughout this whole process. And obviously everyone, Dr. Jeff Berman, Dr. Laura Lowe's, Dr. Michael Olson, everyone at Rapid, just made my experience at Washington very positive. The advice, the technical guidance, and mentorship has just meant so much to me. And then from Georgia Tech, I have some really amazing advisors and mentors who just helped me tremendously. Furthermore, obviously very thankful for Dr. Robin Nelson. And again, I did miss a couple of meetings and being upfront about that, but she's been so patient with me and helped just make this whole program successful. And then of course, thank you to the people that I spent all summer with daily in our dark little office space, and my amazing family who I called again daily from that dark office space, and NSF. Here are my references, and thank you very much.
Hi everyone, my name is Simone. I'm a current environmental engineering student at Georgia Tech, and this is my summer research at the Rapid Research Facility at UW, focused on the dynamic site characterization of soft ground sites in Seattle, looking at workflow analysis and results of the horizontal to vertical spectrum ratio method. So to kind of backtrack and understand the broader implications of what I'm doing, when you think about an earthquake, damage is caused by the earthquake itself, the way it affects the infrastructure, and then also the nature of the site itself, or site effects. Okay, to understand site effects, it's important to know that waves travel through different materials differently. Waves going through bedrock at a high frequency, so these pass quickly and are generally less destructive. Then through softer sediments, these are low frequency waves that pass slowly and are generally more destructive. It's also important to know that seismic waves amplify when they travel from bedrock to soft sediment because they're slowing down and the amplitude is increasing. This is known as site amplification, and this causes more intense shaking. So site amplification, this is common in sedimentary basins as pictured in example of Mexico City. And these are areas that are depressions of land of harder bedrock that have been overlaid by softer sediments over time. And this includes San Francisco, Mexico City, Seattle, our regional interests, and Boston. A textbook example of site amplification is the 1985 earthquake in Mexico City, where areas in the city further from the epicenter were hit worse because of this basin site effect. It's also important to know that structures have a natural period, which are the number of seconds that they naturally vibrate back and forth. And this is the reciprocal frequency. And if the period of ground motion matches the period of a building, it'll undergo the largest oscillations possible and suffer the greatest damage. And so an analogy of this is think about you're being on a trampoline. If you're with someone else and you're jumping, you'll jump higher if you jump at the same time. So when the site matches the frequency of a building, they'll have greater damage, and this is analogous to resonance. Because of this, it's important to understand the dominant period of the site that you're working on. There's a visual of it. So as I've discussed, Seattle is a sedimentary basin, so it makes it more at risk for site amplification, and it also has a lot of artificial fill around the region. and areas, not more natural deposits that are softer of peat from rivers. And many of these areas aren't well characterized in terms of site frequency. So the way that we characterize a site can be found from three methods, and this includes direct measurement from earthquake recordings. And this is difficult in areas that have like low to moderate seismicity because data is limited. Simulation is also possible, but this is both expensive and also has a large environmental impact because we're often drilling, and this isn't often possible in urban environments. So ambient noise recordings are a third option. They're both cheaper and non-invasive to work in. They're really good for urban settings like Seattle. And this horizontal to vertical spectral ratio method predominates as a simple option for ambient noise recording. So what is ambient noise? Ambient noise are all sources of largely surface wave energy on the Earth that consists largely of natural sources like the ocean wave vibrations, but also anthropogenic or human causes like traffic, machinery, or other transient noises that really vary by the time of day and like the city that you're in. And we can learn a lot by recording them. So the way HVSR works is it takes a it records these ambient vibrations using seismometers. This is a picture in green on the left. It records a 3-component ambient noise signal. And from there, we can we take the time window average of the Fourier amplitude spectra for each directional component. And then from there, we develop the horizontal we resolve the horizontal components because there are 3 of them, and then develop the average horizontal to vertical spectral ratio curve. And it's been well proven empirically that the lowest frequency peak, as seen in the bottom center image, can provide a reliable estimate of the site's resonant frequency. As seen on the x-axis, it's about 0.8 hertz here. So in terms of the state of HVSR, the current challenges today are understanding the composition of the microtremor wave field. These can be body or surface waves or a combination. There's a lot of theories about this, but it's not the focus of my research. I'm focused on understanding how many factors and options are involved in the data acquisition, processing, and interpretation stages. So to break this down a little bit, there's a lot of factors, but the ones that I worked on this summer is workflow and analysis. And breaking this down, one really great paper for this is Molnar in 2022. Would recommend it if you're interested in this. So in terms of workflow, we don't have a standard for recording metadata for the HVSR method. And we also have a lot of options for seismometer deployment, which generally increase in preference is seen in the below figure, where buried fully underground is preferred, but not always possible, and this can affect data quality. Then in terms of analysis, as discussed, the horizontal components need to be resolved to develop the HV curve. And this can be done in many ways, though geometric mean is the most widely used. However, calculating this in multiple azimuths or directionalities can prevent the assumption of a spatially homogeneous site. And this is integrated in new processing options called HVSR Pi and its web application, HVSR Web. So as seen, we need to characterize these sites in Seattle to understand site-specific seismic hazards. And HVSR provides a useful tool, especially in this region, for doing so, but it lacks a standardization of workflow and analysis. So this study seeks to perform a site characterization of a local site in Seattle to advance the knowledge of HVSR practices. So the site that I've been working on this summer is Montlake Park, and we've been working here because it's accessible to UW, it's public land, it has previous geotech data that we could compare our findings with. And the research questions I've specifically been working on is what is the spatial variability of site frequency in Montlake Playfield? Within this, are seismometers capable of capturing this variability, and what kind of spacing is required to capture it? And then looking at the actual best practices of acquisition and processing, looking at the workflow of seismometer deployment and also the metadata collection and analysis of HVSR calculation in different processing software like HVSR Web versus Geopsy, and calculating HVSR via geometric mean versus multiple azimuths. So here are the tasks that I did to answer these questions. So first, I kind of learned how everything works. I explored the functionality of HVSR Web, HVSR Pi, and Geopsy. And I also learned how to use the seismometers, and I also developed this metadata structure in the Rapid Facilities app, where I could conduct a questionnaire at every site that I end up doing my seismometer deployment, and this took the actual geolocation from the iPad. So it's really great in practice where I don't have to actually record like where I'm at. I could just like the iPad takes it for me, so it really streamlined that process. And then secondly, I started learning about the site's geotechnical properties by available boring logs on the geologic information portal. And this was supplemented later by a method called MSW, or multi-channel analysis of surface waves. When my advisor came, because it's a really two-person job to complete because it's really heavy. But basically we use active, we use a sledgehammer to generate active sources of waves to ultimately measure site stiffness with depth. And then thirdly, to build on my workflow research, I set up the seismometer in multiple deployments. I buried it, I've set it up on the ground, et cetera, to better understand the effects of deployment setup and processing on the resulting site period. And finally, the bulk of my work consisted of just walking to the park with my wagon and 2 seismometers and passively recording ambient noise with a seismometer in this pretty large field campaign. So I took about 42 data points for 30 minutes across the whole park. So I have a lot of data on this. I can tell you a lot about this park. And here's what I found and what we can learn from this. First, in terms of workflow, these are the HV curves for the different types of deployment that I did. If you look at the x-axis, they're really aligned. The fundamental frequency is calculated using geometric mean, and we found that it was the same for all deployments, about 1.14 hertz, and it was the same except for the one that was directly on grass, which makes sense because it's what we would expect would be the least accurate, because there's nothing coupling it to the ground. Secondly, my results from the analysis, comparing processing the data from the campaign using the geometric mean and also using multiple azimuths using HVSR web, we found really similar results. And we can see that from this, this is indicative of the site has pretty one-dimensional site conditions, meaning it's relatively homogeneous. And then moving on to the actual campaign results, we found from the MESW and site boring data that there was really stiff glaciated soil towards the southeast end of the park and towards like the neighborhood, and then softer soil moving northwards into the park itself. So we would expect here that the frequency would be higher towards this part of the neighborhood, going southeast. However, we had really interesting results from the campaign. We found that there was a really abrupt boundary where the frequency jumped from less than 0.5 hertz towards the southeast, and then had higher frequency in these softer soil areas towards the water, which was opposite of what we would expect. But kind of breaking down a more detailed view of the HV outputs, the spatial trend was really like puzzling initially, but we found that the really short frequency matches the frequency of the surrounding basin. Because the basin is so large, it resonates at a really low frequency. And we verified with some people from USGS that this matches the basin based off of previous earthquake recordings. So that's our current theory for that. There's where the frequency is. And then in terms of conclusions, what can we learn from all of this? In terms of the big picture, as I talked about at the beginning, if an earthquake were to occur in this park, we could expect a higher site-induced damage in these softer sites in red. And there's a significant boundary between the two that could be explored more in a more in-depth site characterization. In terms of like the research questions I outlined earlier, we found that the investigated options for workflow and HVSR computation were not very sensitive. And that shows that HVSR data is relatively robust, even in non-ideal environments, such as measuring like on concrete. So that's really useful if we want to do more like data in more urban environments, but more information might be needed for more complex sites to draw conclusions about azimuthal variability versus geometric mean. Then from the campaign itself, we saw a clear spatial variation that indicated a threshold that showed the seismometers are capable of capturing the spatial variability without having to be too granular of microresolution, because we used 30-meter spacing. So it was pretty, the initial spacing that we did was sufficient. And if we wanted to explore more of this boundary of the glaciated soil and softer peat, we could do this with like a smaller grid. Then in terms of future research, we've joked that we could spend the next several years continuing to work in this park to understand everything about it. But really, we're interested in applying this methodology to all the different soft soil sites in Seattle. And I believe people will be doing this next year. And my personal next steps are to make sure that my methods are replicable by documenting and making sure that all my data is available within Rapid and Design Safe. In terms of my takeaways from this project, I gained experience in a really geotech focused project, which is really interesting and really new to me. And I think it's one really takeaway from this is that I think it's amazing that we can like basically listen to the earth and gain a lot from it. I love doing field work and it really validated that I wanted to do it as a career. And I really liked applying my previous GIS experience to it. And field work is hard, and I realized you need some protection and things like that and have to deal with people sometimes, so it can be challenging, but it was really rewarding overall. And my project can be used to mitigate natural hazards as effective, non-invasive site characterization practices can improve data robustness, and it can ultimately inform hazard mapping. And after NHERI, I'm graduating in December, so I'm in the midst of doing graduate school applications. And in the future, I'm ultimately interested in doing like disaster reconnaissance, and also, but mainly working on doing community-centered engineering approaches. Yeah, and some photos of my experience at the Rapid facility. I have a lot of photos of me with the wagon because that was a lot of my work, was walking to the park for the first several weeks and like getting lost. Like one day, I didn't realize there was a drawbridge, and that was kind of and then one really great highlight of this summer was getting to do work at the Rapid workshop. So I got to teach people how to use the seismometers. And it was also just really great to get to meet everyone from different universities and researchers, and also work with the people at the Rapid research facility. And here's some other pictures outside of work. I got to meet up with students from OSU. Living in Seattle was awesome. I got to live in a co-op that was really fun. And I got to work with Allison and Kelly, who are awesome. And I rented a car for the first time. So that was an also exciting part of my experience. In terms of acknowledgements, this was supported by NSF. Special thanks are extended to Dr. John Hubler and Jill Wortman for their guidance on this research project and data collection. Specifically, Dr. Hubler for doing the MSW with me. Thank you also to the Rapid Research Facility staff for instrumentation training. Andrew Lida helped me a lot with this, and mentorship by Laura Rose and Jeff Berman. And also my advisors at Georgia Tech who helped provide recommendations for this program, Brian Woodall and Bryce Clark, and also Dr. Nelson for flexibility and care throughout this whole summer experience. And these are my references. Thank you. Yeah.
So like, it seemed like it was kind of hard to collect data, like you had the wagon and like the sledgehammer. How applicable do you think this is in the field, as in like, you know, maybe if there's like a, I don't know, you know, a small lot of soil in the middle of an urban area, like how applicable is it to sites like that?
You said small site where?
I'm just saying, like, you were in a park.
Oh, yeah, versus like a concrete area, or?
Yeah, but
yeah,
like, well, obviously, like for the concrete, like pretend that there, if there's a little soil, but you know, it's not in a park.
Well, the stuff I was using, the seismometers were actually, they're pretty transportable compared to a lot of the other instrumentation. Like they've been flown to New Zealand before. And I was limited by the fact I didn't have a car. So it's like the fact I was able to do this just by walking to a park was pretty like, it shows that it is really possible. But and also Nanometrics is a company that makes the seismometers, and they're working on making a lot smaller seismometer systems so that in the future, people, it would be a lot easier to transport the system. It's normally, it's like, well, I guess you saw pictures, it's kind of big, but yeah. Does that answer your question? Or, yeah. Okay.
Hi everyone, I'm Keely Petrowski. I'm a student at Texas Tech, and this past summer I've been at UW working on reconstructing historic masonry buildings using point clouds. So the site that we're focused on is in Mayfield, Kentucky, where on December 10th, 2021, during the Quad State tornadoes, an EF4 tornado tore through downtown Mayfield, which is on the National Register of Historic Places, which you can see a map of it here with the outline of where exactly this district is. And then on the right, there is this image from after the tornado, kind of showing the damage. So some of the buildings completely destroyed, some of them were damaged, so you can see the variability there. So for background, in this historic district, a lot of these historic masonry buildings were damaged, and there's little knowledge on how these buildings behave when subjected to tornadic winds. And ASCE codes for tornadic wind loads, kind of hard to say, do not apply to a considerable number of historic buildings. So that's why it's important for us to model these buildings so we can start learning how they behave. So the information on these buildings was gathered by the FAST team back in December. And they did this using drones and LiDAR. So for the drones, you're able to once you take the images from the drones, you're able to use structure for motion to create point cloud models. And basically what structure for motion is you have this object here, and by the movement of the drone, you're able to take 2D images and overlap them into a 3D model. And then Allison did a great job of explaining LiDAR earlier, but just to recap, it's sending out pings, they reflected, it knows the time and the distance, then you get the scan of the area. And then the FAST team also collected data using handheld Canon cameras, which also use structure for motion, but for my particular study, I did not use those images. And then something I want to point out is the different perspectives of drone and LiDAR. So if the drone obviously is in the air, well, the LiDAR is more on the ground, so they capture different perspectives. So what is a point cloud? Because that's what I'm doing in my models. So a point cloud is a collection of points connecting a coordinate system which represent a physical object. So the drone, sorry, I'm backtracking. That's an example of one of the point clouds I made. And as you can see, as we zoom in closer and closer, you can see the millions of points that make up the building. And in my study, we're seeing that the drone and the LiDAR point clouds complement each other because of the different perspectives, which we'll go into that. So I created the models using 3 different softwares. So I used Pix4D Mapper to make the drone SMM point clouds. I used Leica Register 360 to turn the LiDAR scans into point clouds. And then I registered the 2 together in Leica Cyclone. And I did all of these steps for 12 buildings. So here's Pix4D. So again, this is the drone point clouds. And also in this software, you need to geo-reference the point cloud. So this is done using ground control points, which are points that the FAST team logged while they were at Mayfield. So they're just points with known coordinates, and you're able to connect it to the model. And this helps accurately scale the model so it's usable. And then here's an example of what the point cloud looks like when it's done. And I want to point out, if you look on that tower, you can see gaps in the data right below the overhang where the drone was not able to see. And then Register 360, this is where we're aligning the LiDAR scans. So if you can see the image on the right, every single color in that is a different scan that had to be aligned with each other to create the building. And then again, here's a comparison of what a Pix4D point cloud looks like next to the LiDAR point cloud once it's done. So you're able to see the differences in what they're able to collect. Again, there's the gaps in the data under the overhang on the drone point cloud. And then on the right, you can see part of the roof in that tower you can't really see. So that's where the gaps in the LiDAR data come in, just because they're ground-based. And then in Cyclone, this is where I'm aligning the 2. So I'm taking those pieces of the LiDAR point cloud like we saw it in Register 360, and I'm aligning them with the corresponding part in the drone point cloud.
And here's kind of an example of what that looks like from the top. You're just trying to find all those little walls and corners that actually align with each other. And here's another view of what that looks like. So the top is the LiDAR and the bottom is the drone. And so I'm taking that little chunk and putting it on its corresponding spot there. And this is called a constraint. And every project would have several constraints like this. So every single one of these is something like I just shown before that I have to align together to create the final model. And on the far right, that's our error between the clouds. So we want to minimize that error as much as possible, just because that's how we know that the walls are aligned and it's an accurate model. But we found that this table, not always completely accurate. So we have to rely on cut planes, which is essentially just a slice taken out of the building. And the reason that we found we had to do this was because vegetation can cause that constraint table, like I showed you before, to have a higher error. And this is because when the data was taken, it was slightly windy. So any vegetation was moving around. So then when you go to align it, you can't, because all the leaves are like different directions. So we used cut planes to see that the building itself was actually aligned instead of just relying on the table because you couldn't. So as you can see right there, that's one of the cut planes. Every single color in it is a different constraint. So what you're able to do is zoom in super, super, super close, and you're able to measure the distance between different colors to see what the actual local error on that wall is. Yeah, so very important. And this damaged side on the left, it lines up with the top right of the cut plane. And then here is all the steps together. So this is one of the buildings damaged in Mayfield. Top left is one of the drone point clouds. You can see gaps in some of the walls. Bottom left is the LiDAR point cloud. There's no roof. And then once you put them together, you get that final, more complete model. So for the results, I had 12 complete geographically accurate point cloud models. And here's an example of one of them, the church that we've been looking at almost this whole time. If we were in the program, we could zoom around, zoom in really close, see all of the details. So again, to recap, vegetation can really cause the error in the constraint table to be high, which is why we need to rely on cut planes. Something else important is the time it takes to make these models. I would say minimum 15 hours, but some of them were more depending on the degree of damage. And then we didn't know about the vegetation at first. That was something we kind of learned as we went along. So time is very important. Big takeaway, you have to be patient. Yep. Again, so in conclusion, UAV and LiDAR data can be combined into a complete geometrically accurate point cloud model. And then here on the left, you can see an actual drone image acquired by the FAST team compared to what the final cyclone model looked like. I just think it's super cool how much they look like the picture. Still super cool. And then what's next for these buildings? They're going to be used for structural analysis so that we can begin to learn how to retrofit historic buildings for hazard mitigation as well as historical preservation. And here's another example of one of the buildings that I made. Here are some pictures from my time at UW. I had a really great time. It was also my first time on the West Coast. And flying to Washington was actually my first time ever in a plane. So kind of scary, but it was fun. So I had a lot of fun with Allison and Simral. Another highlight was when we went down to Oregon to visit Matt, Allie, and Nick. It was super fun. We went to Portland and saw waterfalls. Also my first time seeing a waterfall. A lot of first time things this summer, but it was super fun. I really liked UW. Here are my references. And then I'd also like to thank NSF for funding this research. And special thanks to my mentors, especially Sanchi, because I got stuck a lot making these models and she was basically always on call to help me out whenever I needed it. Thank you.
Any questions? For applications like structural analysis, what's the benefit of a point cloud as opposed to just the drone photo that you showed? Like, that looks so much like it?
Hey everyone, I'm Nick Mesa. I am a senior at the University of Florida, and this summer I spent my time at the Oregon State University Wave Research Lab, investigating wave structure interaction during post-earthquake events using real-time hybrid simulation. So,
Spacebar.
all right, so for some background on this topic, we're all well aware of the catastrophic and deadly nature of earthquakes and tsunamis. However, there's a pretty big disconnect in terms of the catastrophic nature of these natural disasters and how much modeling and research has gone into investigating both of these combined. And the reason why they're so difficult to study on a model sense is because we have two different loadings that are governed by two different scaling factors. So let's say if you were to scale down a structure using Froude scaling, which is what we use for hydrodynamic loads, that would lead to incorrect similarities on a seismic and structural scale for the earthquake. Yeah, for the earthquake. So this is solved by using real-time hybrid simulation. This is one method we can use. And RTHS is defined as essentially subjecting a scaled down piece of a larger system to a physical load and then implementing that other load in a numerical sense. So then once we have that physical load, we can kind of scale it up and then apply it to the numerical model. And there is some precedence for this. It has been used to solve the Froude-Reynolds scaling conflict when it comes to wind and wave loading on offshore wind turbines. Okay, sweet. When it comes to our motivation and research questions for this project, think of it as like those nesting dolls, right? There's three different tiers. The most basic one being, how does pressure on this test specimen change if a wave breaks before, during, or after, relative to the actual specimen? Once we have this, we can kind of test these three different situations where that pressure should vary. Once we can kind of test this and have those different pressures, we can then investigate using that variability if we have these different pressures, how does that integrated pressure compare to the measured load on the numerical sense that we're applying to the model? So of course, pressure is force over area. So if we just multiply the pressure by the area of the cylinder's diameter times the height, then we can integrate that and compare it to the numerical loading. And then these two questions are used to then answer the main question of, is RTHS an effective and accurate way of modeling the seismic wave structure interactions? So regarding our materials and instrumentation, this is a picture from the 2021 experiment. I'll get into this later, but we had three different trials in 3 different years. So 2018, 2021, and this past summer. So as you see, the label number 1, that is our test specimen. So for this trial, we were modeling a scaled down bridge column from a 2 or 5 span bridge. This cylinder was connected with thing labeled number 2, which is a hydraulic actuator. This is a robotic arm that served 2 purposes. So it measured the loading that the cylinder received. So as we sent the wave down the flume, it measured the loading from that. But at the same time, it also had to apply the boundary conditions of the numerical model to the cylinder. So in the numerical model, we kind of simulated if this entire bridge was already subjected to an earthquake. So obviously this bridge would be damaged and not maybe act the same as a regular bridge would. So it served 2 different purposes of measuring and applying. It took me like 2 or 3 weeks to understand that, and I still kind of struggle with it. But we also had some wave gauges on the side to kind of measure the free surface of the water. We had some load cells also on the hydraulic actuator to measure the loads being applied. And at the bottom, for our own sake, to make sure it was running smoothly. We also had some pressure sensors along the front face of the cylinder when the waves came in. We also had an LVDT which measured the displacement of the cylinder. Here's some more pictures from this year's experimental setup. So on the left, we actually have that test cylinder itself. And here we can see those pressure sensors along this front loading face right there. And then on the top right, one of the cool parts of this experiment was the first couple weeks I got to design using AutoCAD a plexiglass casing for the hydraulic arm. So previously, when we would run it in 2018 and 2021, there was some oil leaking into the flume, which is obviously a big problem. And also, when you have more than 1 meter waves crashing into the cylinder, everything gets wet. So we use that to protect it, and that was a pretty cool experience. And then the bottom right just had some of the instrumentation used for the experiment. I keep on talking about this cylinder, so here's a little diagram of it. Here we have the kind of distribution of those pressure sensors. So let's point this out over here. Right on this side, on this left side, those are the 6 or 7 pressure sensors that will be measuring the wave impacting the cylinder. We also have some around the circumference of the cylinder, and we'll also take those into account. Overall, this is about 3.5 meters tall. So keep on talking about these 3 different years of experience. That figure on top just kind of shows where the cylinder was relative to each other in each year. So in 2018, it was the furthest down the flume. So theoretically, the wave is broken and it should have the least amount of energy impacting the cylinder. This past year, we had it in between the 2 years. So we tried to have the wave breaking right on the cylinder. Theoretically, that should have most impact, force, and pressure. In 2021, we had it, the wave still intact, unbroken. So that should be in between. After we ran these experiments, we used Python to compile the forces and the pressures measured from the load cells and the pressure sensors. And so to answer that first question proposed about how the pressures vary with the changing locations, we're going to evaluate how those force and pressure values change over time with the varied wave breaking. Again, that's just to manipulate those variables to give us different cases. And then for that second question of comparing the integration versus measured pressure or measured force, we're going to integrate those pressure values, again, using the P times A, and then around and along the test specimen, and then compare that to the maximum pressure and the time series of the force on the numerical model. So if you're bored, sleepy, or feeling a little tired, here's a cool wave video that we took. That's fun. And also the best part was, so this testing ran in the last 2 weeks of July, and that just happened to be like the worst heat wave in the Pacific Northwest of the summer. So what I would do is I would get into the splash zone, and every 15 minutes we'd run a wave. I got in there, got wet, had my quick dry pants on, cooled down, and then we moved on. So that was kind of nice. That place is not AC, it's like a greenhouse, so it's definitely a little bit uncomfortable, but it's nice to have a little tool there too. Okay, I'll also preface the results by saying that because this was the last 2 weeks of July, we were processing data as of last week while we're preparing for the symposium. So this is still very much a work in progress. For that first research question of how the pressure on the cylinder changes if the wave breaks before, during, or after, we can't say there's no really conclusive results right now. We're not sure why, but I mean, for sensor 5, which would be the second highest on the cylinder, it kind of made sense, right? So 2022 being in the middle, the wave broke on it, should have the highest pressure, highest force, and we did see that. But theoretically, 2018, which should have the most dissipation, came in second, and 2021 third. But this isn't consistent throughout all the sensors either, which theoretically it should be. So we're gonna try to figure that out over this next week or so and see why that is the case. And then with those, with that sensor data, we were able to do a preliminary integration of that pressure. So the quickest way to do it was essentially do a projection onto a rectangular plane parallel to the cylinder. This is most likely an overestimation, so that's why I have not compared it yet, but I'm just trying to show you guys, I guess, what the thinking is and what we'll do over the course of this next week. So yeah, that's currently under investigation, and we'll try to optimize that over the next few days. And then finally, as to that last research question, so far, preliminarily, we can say that RTHS is a pretty accurate and effective method at modeling the seismic wave structure interactions. This graph here shows the measured load from the data acquisition system compared to the simulation. And we can see that at least over time, it follows it pretty well. Obviously, there's some gaps in the data there, but that's mainly an issue of scaling. So you have to make sure that the loads are scaled correctly, like I mentioned earlier with the Fruit scaling and stuff like that. In addition to the fact that there's some sampling rate issues. So I believe we use 1/2048. One measurement for every 248. 1/248 hertz, basically. So we have had some problems matching that up, but we'll figure that out again over the course of the next week. Okay, in conclusion, there is no conclusions yet. But again, we can say that RTHS so far is an effective method for modeling the seismic wave structure interactions. We'll say this too, to our knowledge, OSU is one of the first groups to actually model the wave seismic structure interactions. So with that being said, you know, being trailblazers, there's a lot to learn as we go on exploring this topic. And actually, this week or next week, we're starting a new project in directional wave basin on that wind and wave loading on offshore wind turbines. So similar method, just on a different structure with different load. I did a lot this summer in the Pacific Northwest. I made sure to take advantage of going across the country. So yeah, we did a whole bunch of stuff, lots of national and state parks. We went to Crater Lake, went to Silver Falls in Oregon, visited the coast, went surfing for the first time, which was really fun. Very cold compared to Florida beaches, but still pretty cool. Lots of work in the flume. I got to go in the waders and actually fix the mechanical arm, and it was just pretty cool. And awesome time with my fellow interns, Matt and Allie, and also meeting up with the University of Washington interns, Keely, Simran, and Allison. Got to see a baseball game in Portland, Seattle. So really cool and fun stuff. As for our learning outcomes, looking at RTHS in a broader application of natural hazards research, we can kind of apply this to wind and wave research, as I mentioned, with offshore wind turbines, but also we can approach this in terms of tropical cyclones. One of the cool things about this experiment for me, or this project for me, is that I'm also currently working with the NHERI Niche project with the University of Florida and Oregon State, and that applies, we're approaching the scaling issue from a different area. We're looking at testing structures in full scale rather than combining physical and numerical models. So it's been really cool to kind of explore this scaling issue problem from two very different perspectives. I'm looking forward to coming back next semester and applying that learning. As for personal takeaways, this internship has really shown me the value of networking and absorbing the insights of others. Those weekly meetings with industry and academic professionals has really meant a lot, and I'm looking forward to applying that as I apply to grad school this fall. Also, this experience has pushed my limits of comfort and knowledge. It was a bit intimidating to travel, 3,000 miles across the country to different coasts, but it's been the best summer ever. Doing all, learning so much and having all these experiences. And finally, just, understanding the value and importance of the structure and the work-life balance. I think all those questions to the industry professionals about work-life balance, most of them were from me, and it was pretty cool to hear what they thought, and also their lessons to how to apply it now. As for my future, I will be graduating from the University of Florida in spring 2023, the BS in Civil Engineering. I'll be continuing my pursuit of the future in natural hazards research. I think tropical cyclones, we'll see. And yeah, so this fall, I'll be continue working with the NHERI Niche project. And I think I'll be working with Boro's project with the Sentinel project at UF. So hopefully chase down some hurricanes, which again is my life goal. As for acknowledgements, I just want to thank all my mentors who pushed me to be the best person, student, and scientist possible, with specifically Dr. Pedro Monaco and Dr. Robin Nelson. Thank you so much for all that you do. You made this experience 100% better. I've also want to thank my mom, dad, and sister, and all of my family and friends who have supported me throughout my education and this summer experience, again, with those daily calls. And finally, I just want to thank NHERI and National Science Foundation for this incredible research opportunity. So references. Yeah.
Very good.
Said that there was a heat wave or something like that. How much of a heat wave is that?
So I didn't understand. It's like, I'm kind of used to like hot weather, but there's no AC in the Pacific Northwest. So that makes everything like twice as bad. So temperatures are around like 100 degrees, but it's a lot worse when there's no AC. And then when we're working in the wave flume and you have like pants on, it's just like you cook in there. So it was pretty intense, but it's okay. Character development.
Did you get to learn about the numerical model that is it done? It was already completely developed, right?
Yes, and I got to help with calibration and stuff. I'm not a computer person too much. So I was able to learn a few things, like we tried this one method with parallel processing with like splitting the cores to help it actually run in real time. That's the most I know, but I got some experience, which is cool. Thank you.
Well, hi, I'm Allie. First of all, excuse my voice, I'm not sick, I just talk a lot. But I'm Allie and I'm an undergrad at Brown University studying geophysics. And this summer I was at Oregon State University analyzing the wave energy dissipation underneath a floating vegetated mat via optical motion tracking. So just as some background, as climate change progresses, there's increased coastal risks that communities across the country and world are facing, such as rising sea levels and worsening storm surge. And there's two general approaches that coastal engineers take to these problems. There's traditional, the traditional approach is called gray infrastructures because they tend to be concrete based and gray in color. Some examples are in this lower row of the graphic right here. And gray infrastructure has been used, for like centuries, centuries. It's definitely effective, but extremely costly, disrupts the environment. There's a lot of downsides. And growing in popularity in recent years is green infrastructure, which leverages the surrounding ecosystem and sometimes just inserts a new ecosystem in there to fulfill the same purposes. That purpose being coastal wave attenuation, which is a good vocab word here. That just means that after the wave passes through the structure, the height is less. And that's really important to protect against erosion and flooding. So green versus gray coastal infrastructure, there's a lot of interesting benefits and differences. There's a lot of benefits of green infrastructure, such as sustainable building materials. They're definitely much cheaper and a lot less disruptive to the ecosystem. But there's a downside, which is that there's a time curve. You have to wait for the ecosystem to grow. For example, in the case of mangrove forests, mangrove restoration is a type of green infrastructure. Now, the flip side of this growth is that over time, in the long run, where gray infrastructures will degrade over time, green infrastructures grow stronger over time. So when you look at it from a large time scale, there's a huge benefit to green infrastructure. So that's an interesting conversation happening in that field right now. One such green coastal infrastructure is called the Emerald Tutu, which is a project I was working on this summer. It's head up by a team at Northeastern University, my advisor, Julia Hopkins. The Emerald Tutu is a nature-based solution for coastal wave attenuation that takes the idea, all the benefits of nature-based solutions, and seeks to make it portable and easily implementable in urban areas. Because maybe mangrove forests are more difficult to grow in Boston Harbor, but they actually plan, like the Emerald Tutu, their vision is to implement it in Boston Harbor. Here's a digital rendering of this overall vision. So the Emerald Tutu is a system of interconnected floating vegetated mats. So think of these as little islands. They have vegetation on top and underneath, and there's plant growth underneath. That's a very important aspect of the structure. So the two most important aspects of the structure are the vegetation underneath and the fact that this is an interconnected network of floating islands. So those are the two mechanisms that wave energy is dissipated via. Because as a wave approaches the structure, it has to lift all of these mats. So there's a transfer momentum, and because they're interconnected, some energy is dissipated via the tension of the ropes connecting these islands. So the Emerald Tutu team in 2021, they studied the network effects. So they studied that macro aspect. They studied how different configurations of just generalized floating mats would affect the wave attenuation capabilities of the overall structure. And they found some really interesting design insights. My project this year is focusing on the individual mat. What are the mechanisms and maybe some possible design insights we can gain from looking at how the individual mat behaves in waves and what's important for wave attenuation. So that's some background, and there's more background. some important theory that will come up throughout this presentation. According to linear wave theory, water particles in a wave travel in an orbital motion. And fundamentally, the purpose of coastal engineering structures is to disrupt this perfect orbital motion. Therefore, any motion that is not this perfect orbital, theoretically, well, actually, just straight up facts, if it's not in the perfect linear orbital, it's inherently nonlinear. And that means that it's representing something else. That something else is the wave energy dissipation. So this is the theory that my entire project was based off of, this nice visual way of thinking about it, that a perfect undisturbed wave will have a perfect orbital, a perfect undisturbed elliptical orbital. And when a coastal engineering structure disrupts that, the resulting orbital the difference between the perfect and the resultant orbital should roughly be equivalent to the wave energy dissipation. So this is how I decided to quantify wave energy dissipation in my project, because that's what I'm seeking to analyze for design purposes. So the methods. I did not build the Emerald Tutu, but the Tutu team did, and they did a wonderful job. So they brought the Emerald Tutu to the large wave flume at Oregon State University, which is pictured in the middle right there. It was subjected to regular wave conditions, regular non-breaking wave conditions, because we're looking at linear waves. We just want to have the most basic scenario. They built a full-scale prototype of the Emerald Tutu. In the field prototype, it was 3 meters, and in the lab, it was 2.74 or 75. So because I was looking at the vegetation underneath the mat, which is the primary mechanism of wave energy dissipation for the individual mat, we utilized a system called Qualisys, an optical motion tracking software, which works by attaching lightweight little reflective balls. And you just attach them, and there's a system of cameras, and the Qualisys system will track the XYZ coordinates of these reflective markers, and you can analyze the XYZ coordinates from that. So in this experiment, we attached markers to, as exhibited in this schematic, to 3 strands of kelp, which is the vegetation underneath the mat, 3 strands of kelp, amongst many other strands. We tracked 3, and that's the data that I based my analysis on. Oh gosh, okay. Cute. I think I can work with this still. That was nice and dramatic. Oh, perfect. Okay. So this is the experimental setup. We have the constants on the right. And as you can see, there's like 3 general locations that the data was tracked for the kelp strands. So this in the flume was the same strand, but like in between trials, it shifted a little bit. So that's why you see multiple strands there. But yeah, so for my analysis, the variables that were different as I tracked each ball at 3 different locations along the mat. At various different heights, and 2 different wave periods of t equals 2 seconds and t equals 4 seconds. So I talked earlier about how the wave energy dissipation is quantified by as the difference between the perfect and the resultant orbital. So that's called residual function RT, some mysterious residual function RT that I want to get some information about. So in my analysis, I ended up using the velocities because that's going to be overall, that was just the best way to approach the data, and the same exact theory applies. So here's an example. This is one ball from one trial. This is the expected wave orbital, the perfect ellipse based on the height and the tank and the wave period that we sent it at. And then that's the resultant ellipse that was recorded by Qualisys. So this is what the whole methodology was based on, because we saw these orbitals and we were like, ooh, those are not ellipses. There's something going on there. And Yeah, so that's the methodology. And here's the overall data. So first, the position orbitals, this is kind of the raw data. This is all I was able to process was this number of balls. As you can see, there's a lot going on here. There's a lot of variability. Just taking it most basic, between t equals 2 seconds and t equals 4 seconds, the behavior of the kelp is obviously different. This one, well, like you can see, it's like, what are the differences between these two pictures? There's a lot going on here, but another thing that's important to notice is that like the shape is different in different kelp strands, and but there's definitely orbital motion going on here. So this is data that we can work with, and I find these beautiful. Okay. I also find these beautiful. This is the kind of round 2 of data processing. These are the velocity orbitals of every single ball in every single trial. And you know, just a reminder of what's going on here. So there's some really interesting things going on here. T equals 4 seconds is a little bit easier to process. Those are, you know, some circles or something, you know, easy to interpret. These kind of look like figure eights. There might be something going on here with camera angles. It's hard to tell because I reduced this to 2 dimensions because the direction of wave propagation, the movement there, like we don't need to know that much about it. So there might be some camera angle things going on, but that doesn't affect the analysis. I'm not really saying things that are important to the conclusions right now because they're beautiful. I think that one's my favorite. These kind of look like Pringles, teardrops. And also the fact that I just kind of tried to characterize those orbitals, that's a future area of research. It would be interesting to characterize, like, why are these shapes, you know, what is that pattern? So that's something I wasn't able to get enough data to, like, you know, categorize like that. But that's just an interesting thing to think about. So the way that I did analyze this is staying laser focused on the wave energy dissipation. And so I calculated the residual function RT for every single ball in every single trial. Here's one example. I was surprised initially, but then remembered linear theory and was less surprised to see that it's a sinusoidal residual function for every ball in every trial, and it's the same amplitude. We're gonna do a fast Fourier transform to condense the parameter, but so I decided to condense the residual function for every ball in every trial to a single parameter so that I can actually analyze them across. And the parameter I ended up deciding on is just the amplitude of the residual function. There's some interesting findings that we found. So one graph, like before I talk about the graphs that show things, one variable that I did not include visually because it showed no statistical correlation is amplitude of the wave of the residual versus distance from the edge of the mat. So it was found that there's, like, it doesn't matter. The distance from the kelp from the edge of the mat had no effect on the amplitude, which again is a proxy measurement for the wave energy dissipation. And that was surprising visually because the orbitals looked very different, but the residual overall, the difference, like, was the same. And that's important for design because, you know, maybe one might think that the closer it is to the wave, the more like it's receiving that wave and then it dissipates the energy more, but that's not the case. So that was interesting, but the graph didn't say anything, so I didn't include it. And the other 2 variables that were changed is the period. So we can't draw any real conclusions from this because I was only able to test 2 periods, so I only really have 2 data points. But for these 2 data points, there appears to be a positive correlation between wave energy dissipation and period. But I want to note that that does not even suggest that we should expect a positive correlation all throughout, because, for example, in the 2 experiments with the network, they found that there was like an optimal period of wave energy dissipation. So their their graph with more trials kind of looked like this, where there was an optimal wave period. So obviously more data is needed to draw any conclusions about that. And my favorite end graph is amplitude versus height. So this shows that there's a negative correlation between height of the ball in the tank and wave energy dissipation, which means that more energy was being dissipated at the bottom of the kelp strands. And that has a very obvious design implication, which is that means that longer kelp should probably equal more overall wave energy dissipation. And more is needed to like confirm that. But so that's the conclusions that I drew from my research. And I only had 3 variables change. And in order to get more insight into design, I would really want to analyze more trials to include changes that they made to the 2-2 configuration. They added, like they had different densities of kelp strands that they tested, things that were held constant in my research, and they also added weights on top to increase the draft of the structure, all kinds of design modifications that is really what this methodology would be most applicable to. So that's an area of future research. And also, I think one of the people on the Emerald 2-2 team at Northeastern is doing their PhD dissertation on developing like some model of every little aspect of the fluid flow. And they might want to use my coordinate data to do that, or, so that's another application of this research. And beyond the Emerald 2-2, this methodology is useful because I found a way to approximate the wave energy dissipation with within the structure, because wave attenuation is just before and after. That's just the wave height before and after, whereas wave energy dissipation, you're able to look at throughout underneath the mat, what is going on, what aspects are affecting it. So those are my conclusions. And yes, okay, I have some nice videos. I'm gonna play them both at once. Hope you can handle it. But Oregon State University, I had a wonderful time. This was the first day of work. They do have this sign in front of the office. It is not a tsunami hazard zone. It's a joke. But and these are some waves that I was just working at my cubicle and felt the entire building shake, and I was like, what's going on? It was this wave. So it was just a really fun work environment. We were able to take a trip to the coast, to the Oregon coast, to see real coastal processes, and saw a gray whale breach, which was epic. I traveled with my fellow interns, saw the Columbia River waterfalls in the gorge, met up with the rapid team in Portland, and what I think is like the most unique aspect, I got to swim in the flume. It was very, very cold. I do not recommend, but it was my dream to tell my friends, oh yeah, I'm getting paid this summer to go swim in a wave pool. What are you doing? So I accomplished that goal. This was when we were reconfiguring the kelp strands for the tests that I didn't reach in my data analysis. And just a little bit like reflections. Based on my Oregon State University experience, so as of 2 days ago, before coming to Austin, I was like, wow, this has absolutely affirmed that it is it is my soul's destiny to get a PhD in ocean and coastal engineering. And then I watched the wind tunnel presentations here. And I can't deny that I can't deny I have a passion for that too. So that is what I'm studying in undergrad. I came to OSU, confirmed that I really love oceans, water, and fluids. And anytime I see anything interesting with the wind, I will probably also confirm that I love that as well. So no matter, I have no idea which path I'm going to take, but this REU program has inspired me to. Yes.
So they have sponsored the niche facility that they're planning right now. That is basically OSU and
it's wind and water in one.
FIU combined. So that would be your dream place. Is my suggestion.
See, Nick and I, we're staying in touch. Yeah. So I don't know I've been inspired to pursue a career in academia. I really liked what they were talking about with the freedom and stuff. So I'm not sure which PhD program I will end up in, but I'm determined to end up in one. My parents are a little bit like, oh, are you sure? You know, but anyways, and I plan to go with the flow. So these are my references, and for acknowledgements, thanks NSF and this NHERI program. I can't imagine a better fit for me personally, particularly with the water and wind. It's so cool, and I'm really, my interest is in the, you know, the human interactions and with climate change worsening. That's what I want to do in my life. So thanks NSF for making this exist. Thank you, Robin, for, you know, everything. And you know, my interns, and particularly Dr. Pedro Monaco, the director of the Wave Research Lab. Let me just tell you, when he organized a field trip to the coast for us to observe real waves. I think anyways, and it was a great time, and he took us out. We were walking on a beach to observe some coastal processes that were happening. It was like an inlet. It was very interesting. And this man, he got on his knees in sand, grabbed a stick, and started drawing engineering diagrams in the sand to show the sedimentation and flow transports. And I was like, could this get any better? So I really had a great experience at my site and with all aspects of this program, and wanted to make sure I acknowledge that. And that's it. Questions?
So you were saying that the energy gets more dissipated with the longer kelp strands?
We think.
We think, but what about, like, have we looked anything about how it's gonna affect the wildlife? Is it gonna be better for them, worse for them? It might be bad.
Yeah, excuse me. So I didn't look at that aspect of it, but the tutu team, which I spent the first week of this whole program, just, you know, that's why I was in the flume. I was just hanging out with them because it was their week to be at the facility. They talked about all aspects like that, and that I was like, this is so cool. They talked about how they were investigating the environmental impacts. They were also talking about the community organizing perspective. They were talking about urban planning and engaging with the community and stuff like that. So yes, the ecology was one of the moving pieces, but I do want to recall that one of the fundamental principles of nature-based solutions is that it is integrated within the ecology. So the plants, like the vegetation on the emerald tutu, for example, should be native to the ecosystem and not be disrupted. So that is something that I'm sure is a good design question that either they already researched and decided that kelp was good enough, or they're going to find exactly what would be the best. But yeah.
If you cut the kelp off, would it float or does it?
Oh, it would float. So it's a floating island, and I mean
with the kelp floater sink. I'm sure.
Oh, with the kelp floater sink?
Yeah.
Okay, so I don't know, but I learned from our coastal field trip. Well, I was working with strips of PVC plastic. That was on the slide, but so that was our approximation for kelp. But I will say on our coastal field trip, we were looking at and pointing things out, and it's kelp on the beach. And one of the types of kelp, it has like a bulb that floats. So that kind of kelp would float. The PVC plastic wouldn't. That's why they were diving in, those poor PhD students. I didn't have to dive in. They were like, it's okay. I know it's cold, but so does that answer your question? Okay. Any other questions?
Has there been much talk about what kind of vegetation to use on the top of them? Is that going to be kind of like a landscape design kind of thing, where it's supposed to be sort of flower baskets essentially floating around?
No, actually, well, I don't know about flower baskets. They'll probably just do grass, because I don't know how flowers would do just kind of in the ocean, especially if it's a coastal wave attenuation structure, but no, that is an aspect of the design. And one of the additional purposes, benefits of the emerald tutu structure that they're pitching to the scientific community, to everyone, is the fact that it's visually appealing. And in the diagram, in the rendering, the artist rendering of like the vision, it had walkways, because they're saying, hey, you know what's better than a giant concrete seawall that's just there and kind of ugly? A nice park that you could stroll through. So that's actually one of the core design aspects of this, is that it's meant to be a public space. So yeah. Any other questions? Thank you.
Good afternoon, everyone. Great presentations from you all, and especially Ali, that was great. So, hopefully I can close this out okay. My name is Matt Latham. I go to Cal Poly, and my research was focusing on wave height and reflection analysis using something called the orbital velocity method for irregular waves. So the goal of this research was to quantify wave reflection, and to do so by expanding an existing method called the orbital velocity method to apply it to treat irregular waves. And the main application of this kind of research is going to be in the laboratory testing and instrumentation setup. I know y'all were like solving the issues of hurricanes and earthquakes, but mine's more of a supportive role, okay? So maybe we could also apply it to structural design and wave energy conversion, but you know, that'll be down the line. So let me kind of just paint the picture for what we're talking about with wave reflection. So imagine you have an incident wave traveling in this direction, and then it encounters a structure like a wall. Well, that's going to generate a reflected wave going the opposite direction. But what you actually observe in this situation is the superimposed wave of both of these components. So the goal of this research is to kind of separate out those two, the incident and reflected wave components, from the superimposed wave you observe. Going into the literature review a little bit, it starts in 1993 with Hughes, who first proposed measuring the velocities at a single point location to quantify wave reflection. Then it picks up in 2018 with McKee et al. And their orbital velocity method. The most recent instance, though, is in 2021 with Wilhite et al. And their application to regular waves. And this is actually the previous NHERI REU student at OSU, of which this research is based off of. So we have a couple research questions that come from this topic of wave reflection. First is, how can we optimize and automate the orbital velocity method for regular waves? And then second is, can we extend that same method to treat irregular waves? Okay, so fair warning, there's going to be a lot of equations and math that come from this point forward, so I'm going to try to break it down for you guys. There's this thing called linear wave theory in the field of coastal engineering, and here are the equations for the horizontal and vertical velocity of waves. So we don't need to go over all these symbols, and I'm going to make it a little easier by taking x to be 0. Let's just focus in on these three. Whoa, okay. Okay, so these are the three unknowns in these equations, hi, hr, and epsilon. That is the incident wave height, the reflected wave height, and the phase difference between them. Everything else in these equations is either constant or measured. Another way we talk about reflection is with a reflection coefficient. So that's basically a ratio of the reflected wave height to the incident, or a percentage. This is kind of what these equations look like visually. They're both sinusoidal functions. They're 90 degrees out of phase. So when one is at a max or min, the other is 0. When you plot them against each other, like on the bottom here, you get an ellipse. And okay, let me take a little temp check here. Who here thought that, or let me say, like, what do you think waves in the ocean are transferring? Is it mass or energy?
Energy.
Energy.
Everyone knew that before Ali's presentation? Show of hands for mass. Anyone before? Want to admit it? Okay, Ali and Nick. Hey, me too. It's you. Okay. Yeah. No, I thought waves transferred mass, but when you can see in this cute little GIF here, is that the water particles are actually not translating. They're just transferring energy and following an orbital motion trajectory. So more theory, guys. Okay. Extending it to irregular waves. Well, irregular waves may have multiple frequency components superimposed. So here's an example. You'll never see an ocean wave like this, but this is a wave signal that has many frequency components. We can put it through this mathematical process called fast Fourier transform, and that just spits it out into the different frequencies and their amplitude. In equation form, it looks like this. On the left side, we have an amplitude and a phase, and on the right side, we have A and B. You can get either from each other. And okay, I'm gonna do a little derivation for you guys here. So let's bring back the equation for horizontal velocity from linear wave theory. Okay, I've just factored out the constant here. Little sidebar, draw this triangle. This is just a trigonometric relationship we can do to relate epsilon and HR. And then if we rewrite the equation for U with these new variables introduced, you'll notice that if we multiply out the constant, these terms now look like the A and B from the fast Fourier transform equation. So that'll be useful down the line for solving irregular waves. Okay, so we also got to go into statistical analysis for this research because we're trying to fit laboratory data with theoretical equations. So we want to do that by maximizing the coefficient of determination, or R squared, with respect to our three unknowns. So we'll do that by taking the partial derivative of this equation with respect to those three unknowns, and it'll spit out these equality constraints. These can be implemented into MATLAB to solve for the unknowns to maximize all these equations. Okay. And we can also introduce some logical bounds on these three unknown parameters that are shown here. There'll also be requirements in the MATLAB program to kind of just help it solve and get a consistent result. Okay, let's jump into the methods and instrumentation. So we only used one instrument for this whole study, and that is the acoustic Doppler velocimeter. It records velocity in all three directions for a wave. And also we used the program MATLAB to solve those three unknowns. I'll just briefly break down how the code is working here. First, it aligns the velocity data with the theoretical equations. It then discretizes each wave cycle and solves those parameters individually. It stores the results and plots them over the number of wave cycles. And if we have an irregular wave, it'll just do that fast Fourier transform analysis first, and maybe we can do the same process to solve those unknowns. Okay, so here's the first set of results. We wrote a MATLAB program to solve for a single wave cycle here and produce those three unknowns from the linear wave theory equations. As you can see, the blue data there is the laboratory data, and the orange is the fitted equation from MATLAB. It solved the unknown parameters here on the left. This is for one full cycle, a regular linear wave. The natural next step of that is going to be to applying it to multiple wave cycles. So we could generate a graph like that for each and every wave cycle, but that'll get super messy. So this graph here is just the results for HI, K sub R, and epsilon for 99 wave cycles. It tracks it over time. As you can see on the top graph here, HI remains constant throughout this whole trial. And that makes sense because that was a setting that they just initiate in the wave maker itself when they're running this trial. So it was set to 19 centimeters, and that's what we back calculated here, just from velocity. As for the extension to irregular waves, it's still incomplete. The top graph, or the top figure on this side here, is an irregular wave. As you might notice, it's not symmetrical about 0. So that means fitting the linear wave theory equations is not going to work. We have to go through that fast Fourier transform process I outlined earlier. And for MATLAB, it naturally outputs the amplitude and phase, or C and phi from that equation earlier. We can convert that to A and B through trigonometric identities. But despite that, having enough equations for unknowns for irregular waves, those equations yielded no solution. So let's talk about all these results. Okay. This study optimized and automated the calculation of HI, K sub R, and epsilon from laboratory velocity data for regular waves. It visually fit the data very well, although we did not calculate a goodness of fit parameter like R squared. But maybe there were multiple solutions that would fit the data well. How do we know this is the right solution? Well, it consistently produced a single unique result. However, the result could be sensitive to bounds and initial guess. It also matched the expected results based on this laboratory test and setup. And finally, I should mention a potential source of error was any velocity that may exist in the y direction. That's the sideways direction in the wave flume. The linear wave theory equations assume that to be 0. Okay, I've hinted at this a couple times now as the program sensitivity. The MATLAB program was relatively sensitive to the initial guess and boundary conditions. We found that the best results were consistently achieved using an initial guess away from 0, as shown in the parentheses here, and with the bounds listed in the method or in the statistical analysis section. And finally, the extension to irregular waves is still incomplete. Like I said, we couldn't fit the linear wave theory equations to the data directly because it is not symmetrical like the linear wave theory equations are. Also, those equations, those derived equations using Fourier transform had no solution. Oh yeah, and these were the equations I was referring to before. We derived A and B, but these are what they actually look like for both directions. Okay, there's a couple simple conclusions we can draw from this research. First is that velocity measurements at a single point location can successfully estimate incident and reflected wave heights. This is still surprising to me that you can use one instrument at a single point location to predict so much about the wave, its initial height and its reflected component, but it's in the math. And then the second conclusion is that we still need a new strategy to extend the orbital velocity method to irregular waves. So for future research, we have a few questions that we still need to answer. One is the one we started with, which is how can we use the frequency domain analysis to solve for HI, K sub R, and epsilon? And the more focused question is, can we make those mathematical equations agree for A and B that I showed earlier? And then the natural next step for that would be, can we extend that same method to irregular waves? And finally, maybe we should just consider adding another instrument in the laboratory setup, such as a co-located wave gauge, to give us more information to solve for those unknowns. All right, that's it for the research, but for my experience at OSU, it was a great summer. Like Nick said, this is top tier summer. This is great. So on the top right here, that's me in the large wave flume. We also went to Crater Lake, Silver Falls, and the Oregon coast where we saw breaching gray whales. But it wasn't all sunshine and roses, because on the bottom here is the time when I went to trial for a $15 parking ticket. I pled my case, but I did lose. Okay, top 3 takeaways. Well, I had never had experience coding in MATLAB before, so I gained a lot of coding skills there. Also, the writing and research skills from the paper, presentation, and poster. But perhaps the most important is the career development skills from all the workshops we had and conversations with peers in the program as well. So, mentioned this in the beginning. How does this research apply to mitigate natural hazards? Well, it's more of a supportive role for the laboratory testing procedure and instrumentation. If this research could successfully extend to irregular waves in more situations, that would really simplify laboratory setup by requiring just one instrument at a single point. Future plans, although I had a great time in this program, I'm going to do a little course correction and pursue a PhD in environmental engineering, specifically in water and wastewater treatment. After that, it's tough to say, but probably a career in academia or research and development. All right, for my acknowledgements, I'd like to thank all the people who supported me throughout the summer, namely Dr. Pedro Lomonaco, Dr. Robin Nelson, my recommenders from Cal Poly, Dr. Amr El Badaway and Dr. Hani Al-Zraei, my parents, and my fellow OSU interns, Nick and Ali. This was a great summer. And lastly here is just the funding disclosure statement, my references, and a thank you to NSF. Questions?
So you said that the equations didn't have solutions. Why was that?
Well,
why do you think?
Yeah, no, it's a good question. Because they're mathematically derived, but it just didn't work with the laboratory data, probably because the linear wave theory equations assume regular waves. So we wanted to apply it to irregular waves, but that was an assumption of those equations from the beginning. We still derived these from math, but if you can see here for A in both directions, they both have, or B and A, they both have this HR sine epsilon component, and those just don't agree. Like that's 2 equations, 2 unknowns, but you can't solve it anyways because they don't agree. Yeah. Yes.
Is there a way to play with like more of a signal processing kind of thing to try to match some of the irregular waves with the theoretical equations, or is it
a different strategy than frequency domain analysis, or a similar for signal processing?
like, is there a way to like because like sometimes when, at least I've heard in the ocean engineering, what they do to analyze a field data, is that they try to like transform the wave so that it shapes more of a like regular wave, and then they try to study that. So I don't know if is that something you guys have considered doing to try to work around the regular waves?
It is, that's a good point, but the problem is that the equations we're basing it off of don't have any offset component, they're symmetrical about the origin, and irregular waves are essentially an ellipse that has just been shifted. So without changing the fundamental equations, there's not really a way that we could incorporate an offset component.
Thank you.
Right.